Good morning and welcome to the National Transportation Safety Board. I'm Jennifer Homendy and I'm honored to serve as chair of the NTSB. With me today are my board colleagues, Member Michael Graham and Member Tom Chapman. Today's meeting is open to the public in accordance with the Government in the Sunshine Act. We're here to discuss the final investigation report of the collapse of the Forbes Avenue Bridge over Fern Hollow, which is also known as the Fern Hollow Bridge, that occurred on January 28, 2022 in Pittsburgh, Pennsylvania. At about 6:37 a.m. local time, the Fern Hollow Bridge, fabricated from uncoated weathering steel, experienced a structural failure that caused it to collapse, falling about 100 feet into Frick Park. It was dark at the time and the temperature was 26 degrees Fahrenheit with light snow. 5 vehicles were on the bridge: a 2013 New Flyer articulated transit bus operated by the Port Authority of Allegheny County, now known as Pittsburgh Regional Transit, and 4 passenger vehicles. A 5th passenger vehicle drove off the East Bridge abutment after the collapse began and came to rest on its roof on the ground below. 4 people were injured in the collapse: the bus driver and 1 passenger vehicle occupant who sustained minor physical injuries, and 2 passenger vehicle occupants whose physical injuries were severe. The NTSB investigative team will walk us through the event in detail shortly. At that time, they'll also show an animation of the precise sequence of events. I'd like to take a moment to address those who were personally affected by this tragedy, particularly those who were on or near the bridge when it collapsed. On behalf of the NTSB, we are so sorry you experienced such a terrifying event. As you'll hear today, the Fern Hollow Bridge collapse should never have happened. Your injuries, both physical and psychological, should never have occurred. I imagine this event was also traumatic for the entire local community, for the people who traverse the bridge every day, who would have been there on the day of the collapse had there not been snow and school delays as a result. Indeed, this event likely touched everyone in Pittsburgh, which is known as the City of Bridges. Now, our goal is not to place blame, but to learn from this disaster, to fight for positive safety change so it never happens again. Not in Pittsburgh, not on any of Pennsylvania's bridges, not on any bridge, period. There are more than 615,000 bridges across the United States. According to the American Road and Transportation Builders Association, or ARTBA, in 2023, 6.9% of all bridges, or 42,400 bridges, are considered structurally deficient, meaning they're in poor condition. This compares to 7.4% in 2019, showing some improvement since enactment of the Bipartisan Infrastructure Investment and Jobs Act. But motorists cross these structurally deficient bridges 167 million times every single day, as well as an untold number of pedestrians and bicyclists. The American Society of Civil Engineers, who gave U.S. bridges as a whole a C rating in 2021, reports, quote, "At the current rate of improvement, it will take more than 50 years, stretching out to the year 2071 to repair all these bridges. This is not a sustainable model. The rate of deterioration is exceeding the rate of repair, rehabilitation, and replacement, all while the number of bridges are sliding into the fair category, and that's growing," end quote. In fact, 48.9% of all bridges in the U.S. are currently in fair condition. Pennsylvania ranks number 6 in the nation on structurally deficient bridges, with 13% of its bridges designated as poor and in need of serious repair. While this is down from 26.5% in 2011, it's still quite high and in need of immediate attention. As you'll soon hear from staff, one such bridge was the Fern Hollow Bridge, which collapsed from extensive corrosion and section loss damage due to repeated failures to act on known maintenance and repair recommendations that were documented in inspection reports from 2005 to 2021. In fact, had contractors for the city of Pittsburgh correctly calculated and accounted for the effects of section loss and other factors back in 2014, the Fern Hollow Bridge should have been closed. With that, it's important that I highlight once again our role here. The NTSB does not place blame. Our mission is solely to improve safety to prevent this tragedy from reoccurring. In order to do what we do, we work under what we call the party system, meaning following a tragedy, we bring together technical experts from those involved in an accident, or in this case, a bridge collapse, to help us gather and develop the facts around the investigation. However, the parties are not part of the analysis or development of the findings, probable causes, or safety recommendations. That is solely the job of the NTSB. But parties are critical to helping us obtain information such as inspection reports, which we need to carry out our critical safety mission. At the same time, parties get access to what we're finding in real time over the course of our investigation, so they don't have to wait until the conclusion of the investigation to make safety change. They can do that early. So I'd like to thank the following organizations for their collaboration with us on scene and their role as parties to our investigation. The Federal Highway Administration, and in particular, Administrator Shaylin Batt, the former acting administrator, Stephanie Pollock, and senior structural engineer, Justin Osell. The Port Authority of Allegheny County, which as mentioned is now Pittsburgh Regional Transit, especially Deputy Chief Sean Hudzinski, the Pennsylvania Department of Transportation, or PennDOT, including Secretary Mike Carroll, who was not secretary at the time of the collapse. He wasn't confirmed until May 2023. He has an extensive background in transportation and infrastructure and has done an excellent job in helping the state move forward. I also want to thank PennDOT's Bridge Bureau Director, Richard Runyon. And for the city of Pittsburgh, Mayor Ed Gainey, who I met with several times on scene. He was mayor for just 25 days before the collapse occurred. He and his staff have worked very well with our team throughout the investigation, and he is very focused, rightfully, on how to move forward to ensure the safety of the city of Pittsburgh's bridges. I also want to thank city engineer Eric Setzler. In particular, I'd like to thank the emergency responders who were out in full force. The Pittsburgh Bureau of Police, Pittsburgh Bureau of Fire, the Pittsburgh Bureau of Emergency Medical Services, the Allegheny County Police, Pittsburgh Park Rangers, the Pittsburgh Regional Transit Police, the Federal Bureau of Investigation Pittsburgh Evidence Response Team, Civil Air Patrol, and the Pennsylvania Public Utilities Commission. I also thank Swank Construction Company for their assistance with the recovery and handling of evidence. And of course, Turner Fairbank Highway Research Center for their assistance testing the bridge steel. Finally, I'd like to acknowledge the incredible people of Pittsburgh who welcomed us on scene and brought us cookies and warm beverages to the entire team. We weren't out in the cold for long, and it was cold. And that's thanks to Waverly Presbyterian Church, whose staff provided us with warming space, meeting rooms, and restrooms, in addition to snacks and water. Thank you all. Now, turning back to the report, each board member has studied the draft report and met individually with the investigative team, but this is the first time we've gathered as a board to discuss the report. In a moment, NTSB staff will present the pertinent facts and analysis and summarize their findings in detail. After their presentations, board members will question staff on the key safety issues uncovered during the investigation. These include a lack of action on maintenance recommendations, the ineffective bridge inspection program, and insufficient oversight of the bridge inspection program. Staff will then propose the relevant findings, probable causes, and safety recommendations for board consideration. Following the incorporation of any amendments voted on today, the final report will be available on our website in just a few weeks. The public docket for this investigation was released on January 25th, 2023, and contains nearly 6,000 pages of additional relevant material. It's available on our website at ntsb.gov. I'll now ask Deputy Managing Director for Investigations, Brian Curtis, to introduce members of the NTSB team that are participating in today's meeting. Good morning, Mr. Curtis.
Good morning, and thank you, Chair Homendy. My only administrative announcement this morning is a reminder for the meeting participants to silence all their electronic devices at this time. I now introduce staff for today's meeting. Unless otherwise noted, staff are from the Office of Highway Safety. Chris Poland, Deputy Director for the Office of Highway Safety. Meg Sweeney, Project Manager. Dennis Collins, Investigator in Charge. Steve Prouty, Structural Engineer. Dan Walsh, Structural Engineer. Adrian Lamb, Materials Engineer from the Office of Research and Engineering. Eric Gregson, Reconstruction and Drone Operations. Jennifer Adler, Director for the Office of Safety Recommendations and Communications. Tom McMurray, General Counsel for the NTSB. Carl Schultheis, Acting Deputy Director from the Office of Research and Engineering. Julie Perot, Safety Recommendations Specialist from the Office of Safety Recommendations and Communications. Tom Barth, Chief, Special Investigations Branch and handling the audio-visual today. Ellen Lee, Acting Chief of the Report Development Division. And Mike Brokus, Technical Writer-Editor for the report. I'd also like to acknowledge staff noted here for their support in the production of today's virtual board meeting. Presentations will begin with an investigation overview by the investigator in charge, Dennis Collins. Mr. Collins.
Good morning, Chair Homendy, Member Graham, and Member Chapman. Today, staff will present on the investigation into the collapse of the Fern Hollow Bridge in Pittsburgh, Pennsylvania. To provide a better understanding of both the bridge and the investigation, staff has created an animation providing a high-level overview. Subsequent presentations will provide additional details on specific aspects of the collapse. Please play the animation.
On January 28, 2022, about 6:37 a.m. Eastern Standard Time, the Fern Hollow Bridge in Pittsburgh, Allegheny County, Pennsylvania, collapsed. At the time of the collapse, there were 4 passenger vehicles and an articulated bus on the bridge. A 5th passenger vehicle drove off the east bridge abutment after the collapse began and came to rest on its roof. 4 people were injured and there were no fatalities. The bridge, which was located about 5 miles east of downtown Pittsburgh, ran east and west and carried Forbes Avenue traffic over Frick Park. The bridge opened in 1973 with 2 lanes of traffic in each direction. The bridge was 447 feet long, and the main bridge structure consisted of 2 large girders, called frame girders, running east and west, supported by 4 rigidly connected legs, and abutments at the east and west ends. Each leg was about 60 feet long and oriented at an angle with respect to the frame girders. Each pair of adjacent legs were connected by cross bracing. This design is referred to as a K-frame due to the way the frame girders and legs form a shape similar to an elongated K when placed on its side. Each leg was constructed of welded steel plates forming an I-shaped cross section. The 2 flanges were the main load-carrying parts of the leg. Each leg narrowed from top to bottom and then tapered to a shoe that rested on a reinforced concrete thrust block. On the inside of each leg, longitudinal and transverse stiffeners were welded to the web and flanges to resist buckling. The outward sides of the legs did not have these stiffeners, but, like the insides of the legs, included a transverse tie plate and longitudinal bearing stiffeners running the length of the shoe. The tapered legs cause compression forces in the flanges to push outward. This outward push was resisted by the transverse tie plate and the web at the top of the shoe, which placed the transverse tie plates in tension. By design, the transverse tie plates were thicker than the transverse leg stiffeners to carry the forces at this critical location in the leg. The bridge was constructed of uncoated weathering steel, an alloy designed to form a protective surface layer of rust called a patina. The patina develops over time through repeated wet-dry cycles. Because a properly formed patina resists corrosion, using this material eliminated the need for painting or coating. This is an overhead view of the bridge taken shortly after it collapsed. A Port Authority articulated transit bus was traveling from west to east on the bridge prior to the collapse. It was equipped with video cameras, including one facing forward at the front of the bus and one facing rearward along the right side of the bus. In the rearward-facing video, the beginning of the collapse can be seen as the railing near the west end of the bridge begins to drop. As the west end of the bridge fell, video from the forward-facing camera shows the east end of the bridge still intact. This video evidence indicated that the collapse started near the west end of the bridge. The Fern Hollow Bridge was inspected every 2 years in compliance with the National Bridge Inspection Standards. Starting in 2014, the Pennsylvania Department of Transportation required the bridge be inspected every year due to its condition rating and 26-ton weight restriction, also known as a posted load limit. Inspection reports over the years repeatedly documented clogged drains in areas where leaves or other debris collected, allowing water and road salts to run down the bridge legs and accumulate on the legs near the transverse tie plates. This accumulation of water and debris on the bridge legs prevented these areas from drying, which, in turn, prevented the protective patina from forming on the uncoated weathering steel. This lack of patina and a continued accumulation of water and debris ultimately led to extensive corrosion damage and loss of material, or section loss, on critical areas of the bridge legs, including the transverse tie plates. The inspection reports documented some of this section loss, which progressed to the point that there was thinning of and holes through numerous structural elements on all 4 legs. In 2009, due to corrosion of the leg's cross-bracing, steel cables were added to both sides of the bridge legs, connecting the top of one leg with the bottom of the other leg, forming an X. The cables were intended to be used as a temporary measure until the rigid cross-bracing could be replaced with new cross-bracing of the same kind. This was never completed. Similarly, a rust-inhibiting coating was to be applied to the bridge legs and lower bracing members, but this was also not completed. Post-collapse examination revealed that while all 4 legs sustained damage, the southwest leg sustained the most damage, including significant fracturing and deformation. On the southwest leg, both the web and transverse tie plate were severely corroded. The thickness of the transverse tie plate was substantially reduced near the hole in the web. These 2 images, taken from inspection reports, show the same hole in the southwest leg in 2013 and 2021. In 2021, the hole in the web above the tie plate was visibly larger than it was in 2013. Following the collapse, 3-dimensional scanning was used to document section loss on the legs of the bridge. These scanned images confirmed the reduced thickness of the southwest leg and transverse tie plate as shown in the photos. The yellow areas indicate where the steel was only 25% of its original thickness. During the collapse, the bottom flange, highlighted in blue, separated from the web and the transverse tie plate, and the flange curled back onto itself as shown here. The bottom of the leg also bent approximately 90 degrees, changing the orientation of the shoe. While these deformations are being shown separately for illustrative purposes, they would have occurred simultaneously during the collapse of the bridge. Post-collapse photographs of these damaged portions of the leg have been superimposed. Taken together, the observed post-collapse damage to the bridge, the reduced thickness of the southwest leg's transverse tie plate as documented in the inspection reports and 3D scanning, and the video footage from the bus cameras indicate that the collapse of the Fern Hollow Bridge began when the transverse tie plate and the southwest bridge leg failed due to extensive corrosion and section loss.
At the time of the collapse, it was dark and the temperature was 26 degrees Fahrenheit with light snow. All injured occupants had been transported from the scene by 8:26 a.m. A 16-inch gas main was severed during the collapse, but no fire or explosion occurred. Staff believes the emergency response to have been timely and effective and has excluded it as a factor. This slide is the first of two slides listing the NTSB personnel sent to the collapse. This is the second slide listing the on-scene staff. This slide lists the additional staff who assisted with the development of the Fern Hollow Investigation Report product. There were 4 parties to this investigation: the Federal Highway Administration, or FHWA, the Pennsylvania Department of Transportation, or PennDOT, the City of Pittsburgh, and Pittsburgh Regional Transit, or PRT, which was known as the Port Authority of Allegheny County at the time of the collapse. Staff identified several safety issues during the investigation. The repeated lack of action on recommendations from the inspections of the Fern Hollow Bridge at multiple levels, failures in the bridge inspection program, which was non-compliant with federal and industry guidance, did not identify all the fracture-critical members of the Fern Hollow Bridge, as well as producing inaccurate load calculations. And finally, insufficient oversight of the bridge inspection program at the city, state, and federal level. Staff will make 3 presentations. Ms. Adrienne Lamb, materials engineer, will present on the corrosion of the bridge, testing of the steel used, and finite element modeling. Mr. Steve Prouty, a structural engineer, will present on all aspects of the inspections of the Fern Hollow Bridge. And Mr. Dan Walsh, also a structural engineer, will present on the load rating, the thickness of the asphalt wearing surface, and the oversight of bridge inspections at all levels. We will begin with Ms. Lamb's presentation.
Good morning, Chair Homendy, Member Graham, and Member Chapman. In my presentation today, I will review the corrosion observed on the bridge components post-collapse, the results of testing of the steel used in the construction of the bridge, and the conclusions drawn from finite element modeling of the bridge design. The Fern Hollow Bridge was constructed from a grade of steel called uncoated weathering steel. Uncoated weathering steel, or UWS, is a high-strength, low-alloy steel developed at the beginning of the 20th century and used commercially for over 60 years. UWS was designed for structural use without the need to use paint for environmental protection. This is because, under appropriate wet-dry cycling conditions, UWS develops a stable oxide called a patina. The elimination of painting makes UWS more cost-effective, but still requires maintenance to ensure the wet-dry cycles are achieved and corrosion is prevented. The proper use of uncoated weathering steel has been addressed by Federal Highway Administration for many years, including a 1989 technical advisory that was highlighted in their May 2023 response to the NTSB interim recommendation. Additionally, thorough guidance has been provided in a 2022 report published jointly by the National Steel Bridge Alliance and American Institute of Steel Construction. Corrosion is an issue addressed at length in that report, including ways to prevent it and how to inspect UWS for its presence. Extensive corrosion with accompanying section loss was observed on all 4 legs of the Fern Hollow Bridge. Section loss refers to reduction of component thickness due to corrosion, with a hole demonstrating an area with 100% section loss. The corrosion was particularly concentrated in the shoe at the bottom of the legs, as can be seen in the photos shown here. Evidence of corrosion included buildup of corrosion products, indicated by blue arrows, holes in the web, outlined in yellow, and thinning of the transverse tie plates, highlighted in orange. Evidence of corrosion was also observed in the leg stiffeners. Longitudinal stiffeners had holes in areas where debris collected at the bottom of the legs, as shown in the photos on the left. Transverse stiffeners had holes along the drainage path from the deck, indicated in the top of the photo on the right. These holes were in line with thinning of and holes in the transverse tie plates, as indicated in the bottom of the right photo. The cross bracing between the legs also had extensive corrosion. The top left photo shows holes visible in a cross bracing end, while the right photos show noticeable deterioration on the connecting bolts and plates that assembled those ends to the bridge legs. To document the extensive corrosion observed, 3D laser scanning was performed on the bottoms of the bridge legs, which had been collected while investigators were on scene. The process merged multiple line-of-sight laser scans into one cohesive point cloud, resulting in 3-dimensional models of each leg piece. The models could be reoriented, enlarged, sectioned, and measured for further analysis. The central photo on this slide shows the bottom of the northeast leg, which had the least structural damage post-collapse. On the left is an image of the 3D model showing thickness of the web. In addition to holes in the shoe and above the transverse tie plate, large areas are visible where the web had 50% section loss, which is half the expected thickness. A view displaying the transverse tie plate thickness shows that it also had 50% section loss near the holes in the web. Shown here are similar images of the southwest leg, which, as discussed in the animation, is the leg where the collapse initiated. While portions of the web were missing from the plate piece due to damage from the collapse, holes and significant section loss in the web are still visible in the shoe. A view displaying the transverse tie plate thickness shows 50% section loss on almost half of the transverse tie plate, with some areas having less than a quarter of the expected thickness remaining. Comparing this to the previous slide, the southwest leg experienced greater deterioration and thus was more susceptible to failure. Design plans for the Fern Hollow Bridge called for the use of uncoated weathering steel that met ASTM specification A588. 26 plates of steel were purchased from 2 different steel mills. Mill test reports, or MTRs, provided by the steel mills listed the tensile strength, impact strength, and chemistry for each plate sourced. The individual plates were matched with material collected on scene, then tested and compared to the applicable MTRs. In addition, cross sections were prepared so plate microstructure and weld integrity could be examined. All testing was performed at FHWA's Turner Fairbank Highway Research Center. A few plates located in the girders, away from the collapse initiation at the bottom of the legs, were slightly below tensile strength, though all plates met impact strength requirements. Several plates had non-conformant chemistry and were subsequently analyzed for any effect on corrosion resistance. That analysis determined the desired protective patina could still have formed under appropriate conditions on all plates. The plate's microstructure appeared as expected, while cross-sections through welds showed some lack of fusion and evidence of section loss due to corrosion. Several welds also had cracks, but none were consistent with fatigue cracking. A finite element model, otherwise known as an FE model, was developed to analyze the collapse of the Fern Hollow Bridge. The FE model simulated the collapse sequence and examined performance of the bridge legs. The overall global model was constructed using the design plans. The specific local behavior at the bottom of the legs was further refined by incorporating the 3D laser scans of the section loss and the results of the material's properties testing. The global model showed that the as-designed Fern Hollow Bridge could support the demand from both the dead load of the bridge itself and live load from traffic, which indicated the bridge design was adequate for its intended use. However, at the bottom of the legs, incorporation of the section loss present at the time of the collapse resulted in a transverse tie plate with decreased capacity that could no longer carry the necessary demands of the bridge. The still image of the FE model shown here illustrates that when the bottom of the leg is loaded, the reduced capacity transverse tie plate would separate from the flange, as indicated by the black oval. This separation was the action that triggered the collapse of the bridge. In summary, there were numerous signs of extensive corrosion on the bridge legs, including substantial section loss of the transverse tie plates that reduced their structural capacity. Therefore, staff concluded that the corrosion-induced failure of the transverse tie plate on the southwest leg caused the collapse of the Fern Hollow Bridge. Additionally, staff excluded the use of uncoated weathering steel, the fabrication of the materials, and the welds used in the construction of the bridge, and the bridge design as factors in the collapse. This concludes my presentation. Next, Mr. Steve Prouty will discuss bridge inspections.
Good morning, Chair Hamady, Member Graham, and Member Chapman. This presentation will discuss several aspects of bridge inspections as they relate to the collapse of the Fern Hollow Bridge and is broken into the following topic areas: the Fern Hollow Bridge inspection reports reviewed by investigators, the findings from the inspection reports and the bridge maintenance actions that were recommended by the inspectors, the safety recommendation report previously issued by the NTSB, the quality of the Fern Hollow Bridge inspections, shortcomings identified in the inspections, and failures in the inspection program, the errors and omissions found in the fracture critical member inspection plans for the Fern Hollow Bridge and how these contributed to the collapse, and the lack of guidance for the proper identification of fracture critical members. The first area we will discuss is the Fern Hollow Bridge inspection reports reviewed by the investigators. Bridges are inspected for three main reasons. First and foremost, bridges are inspected to ensure that they are safe for the traveling public. Second, to determine if maintenance or rehabilitation work is needed to prevent structural failure. And finally, so bridge owners can make informed asset management decisions. The FHWA establishes the National Bridge Inspection Standards, or NBIS, which are codified in federal regulations. The states are responsible for carrying out the NBIS by ensuring that the inspections of all the bridges within their boundaries are performed in compliance with the standards. Within Pennsylvania, PennDOT is the agency responsible for carrying out the NBIS. If a city, county, or township owns a bridge, that municipality is responsible for its inspection. A key term that I will use is fracture critical member, or FCM. A fracture critical member is a bridge component that meets the following three criteria. It is made of steel, it is fully or partially in tension, and the failure of that member will cause the bridge to partially or fully collapse. In the 2022 update to the NBIS, the term fracture critical member was renamed non-redundant steel tension member, or NSTM. As the owner of the Fern Hollow Bridge, the City of Pittsburgh was responsible for making sure it was inspected as required by the NBIS and was also responsible for its maintenance. The Fern Hollow Bridge was subject to two types of inspections: routine inspections and interim fracture critical member inspections. Routine inspections are regularly scheduled inspections that consist of examining and documenting the condition of the bridge and identifying any changes from previous inspections. Fracture critical member inspections involve a hands-on inspection of fracture critical members or member components and may include visual and other non-destructive evaluations. Investigators reviewed all the inspection reports for the Fern Hollow Bridge from 2005 until the time of the collapse. The routine inspections were performed every 2 years and included a fracture critical member inspection as part of the routine inspection. Beginning in September 2014, the Fern Hollow Bridge was also subject to interim fracture critical member inspections that were performed in the years between the routine inspections, reducing the time between FCM inspections to 1 year. PennDOT policy requires interim inspections be performed for any of several reasons, including a reduced load rating or a poor condition rating, both of which applied to the Fern Hollow Bridge, which was posted with a 26-ton weight restriction in early 2014. An additional interim fracture critical member inspection was performed in March of 2018 to follow up on repairs that were required to be made within 6 months of the previous inspection. Each inspection of the Fern Hollow Bridge was carried out by a team of at least 2 certified bridge safety inspectors, one of which was designated as the team leader and is responsible for planning, performing, and reporting on the findings of the inspections. All inspectors of the Fern Hollow Bridge met both federal and PennDOT requirements. In accordance with the PennDOT's bridge inspection guidelines, when inspectors found an item needing repairs, a maintenance priority code ranging from priority code 0, which required an immediate response within 7 days, to priority code 5, which allows the work to be completed according to the existing maintenance schedule or within the next work cycle. Now that we've talked about the inspection process, let's discuss some of the findings and maintenance recommendations made in the Fern Hollow Bridge inspection reports. In our review of the inspection reports, we found numerous inspection findings that were, with few exceptions, documented year after year. The inspection reports also contained maintenance recommendations, many of which were repeated nearly every year. For example, these photographs show the clogged drainage inlets on the bridge deck. Despite maintenance recommendations being repeatedly issued to the City of Pittsburgh, nearly every routine inspection found the drains on the deck to be partially or fully clogged. The one exception is that the 2009 inspection found that the drains had been cleaned that year and were clear at the time of the inspection. But just 2 years later, in 2011, the drainage inlets were found to be clogged again. Another example, here are photographs of the southwest leg taken during the 2013 and 2021 inspections, showing the condition of the transverse stiffeners, which were reported in every inspection that we reviewed. Our last example shows the corrosion and section loss on the cross bracing, which was noted in every inspection report from 2005 through 2021. While none of the cross braces were ever repaired, the lower cross brace at the west end of the bridge was removed in 2018 and will be discussed in greater detail by Mr. Walsh. As a result of the investigation, we found significant corrosion and section loss on the bridge, particularly the southwest leg. Maintenance and repair recommendations were repeatedly made to the City of Pittsburgh, however, they failed to act on them. This led to progressive deterioration and the structural failure of the bridge. Given the condition of the Fern Hollow Bridge at the time of the collapse, investigators felt it was important to issue an interim safety recommendation. As a result, the NTSB issued a safety recommendation report in May of 2023. The report contains safety recommendation H2313, issued to the Federal Highway Administration to develop a risk-based, data-driven process to identify, prioritize, and perform any incomplete follow-up actions on bridges with uncoated weathering steel components. On July 19, 2023, in response to the NTSB recommendation, the FHWA published a memorandum instructing all state departments of transportation and other bridge owners to identify bridges with uncoated weathering steel components in the primary load path and ensure that maintenance items which address deficiencies resulting from poor uncoated weathering steel performance are completed. Additionally, the states are to verify that the current load rating for the bridges are adequate. The FHWA's response to identify bridges with uncoated weathering steel components and to ensure follow-up actions are performed on these bridges meets the intent of the NTSB's safety recommendation. Staff proposes that safety recommendation H2313 be classified closed acceptable action. We will now discuss the quality of the Fern Hollow Bridge inspections, shortcomings identified in the inspections, and failures in the inspection program. Guidance on performing bridge inspections can be found in the Bridge Inspector's Reference Manual, referred to as the BIRM, which is published by the FHWA, and in the Manual for Bridge Evaluation, or MBE, which is published by the American Association of State Highway and Transportation Officials, or AASHTO. The MBE is incorporated by reference into the federal regulations. Several quality issues were identified within the Fern Hollow Bridge inspection reports. First, during a bridge inspection, where possible, corroded material is supposed to be removed and measurements are to be taken on bare metal. Photographs from the inspection reports, however, like this one from the 2015 report, show that corroded material was not always cleaned away. Second, the guidance points out that when inspecting a steel structure, inspectors need to determine the extent and severity of any corrosion and measure the amount of cross-section remaining. Although the bridge inspectors documented some of the section loss and holes throughout the bridge, they did not thoroughly measure and document the thickness of the remaining steel, as precise measurements are crucial to an accurate load rating. Third, inspectors are required to provide a condition rating for the superstructure. The superstructure of the Fern Hollow Bridge was rated in fair condition from 2005 through 2009, and then dropped to poor condition from 2011 until the collapse. However, even those condition ratings did not reflect the true condition of the bridge and should have been lower. And fourth, on the Fern Hollow Bridge, the condition state rating of all four legs was severe, which is the worst possible rating and calls for a structural review. No records were located to indicate that a structural review was conducted as a result of the severe condition rating, nor was any such recommendation made in the inspection reports. Staff found that multiple inspectors failed to perform the inspections in compliance with the National Bridge Inspection Standards, and these failures contributed to the inability of the bridge to maintain its rated capacity. We will now discuss errors and omissions found in the fracture critical member inspection plans for the Fern Hollow Bridge. Under the NBIS, fracture critical member inspections are required to be conducted on all bridges that contain FCMs. FCM inspections are more rigorous than a routine inspection, as the inspection of bridges with fracture critical members are expected to identify defects that, if left unaddressed, could lead to the failure of those critical components as well as the bridge itself. An FCM inspection requires a written and well-documented inspection plan to ensure that all fracture critical bridge elements or fracture critical members are identified in advance and that they are inspected properly and thoroughly during each FCM inspection. Additionally, FCM inspections are required to be conducted as a hands-on inspection, meaning that the inspector must be close enough to all parts of the FCMs to be able to reach out and touch any part of it as necessary. FCM inspections will often include the use of non-destructive evaluation methods to determine the presence and size of cracks or other defects that are difficult to see with the naked eye. Following the collapse, the NTSB and FHWA evaluated the design of the Fern Hollow Bridge to determine whether the rigidly connected frame legs were fracture critical members and therefore subject to the additional requirements of an FCM inspection. During the evaluation, we found that the rigid connection between the main girders and the frame legs would have allowed for the transfer of bending moments or forces from the girders into the legs, and this transfer of bending moments would have added to the bending moments originating in the legs due to their angled orientation. Additionally, a table was included on the design plans for the Fern Hollow Bridge that indicated there would have been bending stresses transferred from the main girders to the rigidly connected frame legs as shown on the slide. This information should have been enough to prompt the structural engineers that were developing any fracture critical member inspection plans to perform an additional analysis to determine if any portions of the leg would be in tension. The results of a post-collapse analysis was able to confirm the accuracy of the axial stress and maximum unit bending stress values for location G in the design plans. The analysis found that under the loads used in the design of the bridge, a portion of the leg's lower flange would have been in tension as indicated by the red highlighted region in the diagram. The remainder of the flanges would have been in compression as indicated by the blue highlighted regions. As presented in the animation, the transverse tie plate resisted the outward forces produced by the sharp change in direction of the flanges at that location, causing the tie plates to be in tension. As we can see here, investigators were able to determine that the rigidly connected frame legs were in tension in two distinct areas: the top two-thirds of the frame legs' bottom flanges, as well as the transverse tie plates, both of which are highlighted in red. Because the non-redundant steel frame legs contained areas that were in tension, the legs should have been designated as FCMs on the inspection plans, thereby subjecting them to the fracture critical member bridge inspection requirements. As we just established, the frame legs were fracture critical members and should have been identified as such. The diagram shown here was taken from the most recent FCM inspection plan for the Fern Hollow Bridge, with the green highlighted areas indicating portions of the bridge that had been identified to contain fracture critical members. The frame legs, encircled in red, were not identified as being FCMs. In fact, none of the inspection reports or fracture critical member inspection plans generated for the Fern Hollow Bridge ever identified the frame legs as being fracture critical members. As discussed earlier, PennDOT has established maintenance recommendation priority codes as a way of prioritizing the maintenance recommendations resulting from an inspection, as well as establishing a time frame within which repairs and other maintenance work is to be completed. This guidance also provides an example for assigning priority codes specific to severe corrosion on fracture critical members and states that full thickness section loss or holes in a fracture critical member should result in a maintenance priority code of 0. As a reminder, maintenance items with a priority code of 0 require a response within 7 days. Because the legs were not identified as fracture critical members, the most urgent priority code rating they received for the full thickness section loss was a priority code of 2. As a result, staff found the following. The fracture critical bridge inspection plans did not properly identify the bridge legs as fracture critical members. As a result, the bridge legs did not undergo an in-depth hands-on inspection, nor were they assigned the most appropriate maintenance recommendation priority code. Had the City of Pittsburgh repaired the legs, the collapse of the Fern Hollow Bridge could have been prevented. The correct identification of fracture critical members is crucial to ensuring that these members are properly maintained so that they do not fail and result in a partial or full bridge collapse. For these reasons, one recommendation is proposed to the Federal Highway Administration to require state departments of transportation and other bridge owners to conduct a one-time review of existing fracture critical member inspection plans for bridges with non-redundant steel frame leg designs to ensure that all fracture critical members are identified. Finally, we will discuss the lack of guidance regarding the proper identification of fracture critical members. Except for the transverse tie plate and the web immediately adjacent to the tie plates, the bottom third of the legs, including the shoe, were mainly in compression. The transverse tie plates at the top of the shoe were critical components in the structural stability of the legs, as well as the overall bridge, but were not identified as FCMs prior to the collapse, nor did inspectors recognize the failure risk when they documented the section loss to the transverse tie plates. Neither the berm nor the MBE addressed the identification of bridge components in localized tension zones, such as the tie plate region of the Fern Hollow Bridge, especially for portions of bridges that are globally in compression. As a result, staff found that the lack of information on properly identifying localized tension zones in bridge inspection guidance materials may contribute to the failure of the inspectors to correctly identify fracture critical members. For this reason, one recommendation is proposed to the Federal Highway Administration, and one recommendation is proposed to the American Association of State Highway and Transportation Officials to include guidance in their manuals that address the identification of localized tension zones. This concludes my presentation. Mr. Walsh will now discuss load ratings.
Good morning, Chair Hamady, Member Graham, and Member Chapman. My presentation discusses several failures that allowed the Fern Hollow Bridge to remain open when its conditions dictated that it should have been closed. I will be discussing the failure to perform an adequate bridge load rating, the failure to measure an accurate asphalt wearing surface thickness on the bridge, and the insufficient oversight by the City of Pittsburgh, Pennsylvania Department of Transportation, and the Federal Highway Administration regarding bridge inspections. This depiction of the Fern Hollow Bridge as designed shows that a bridge load rating is the process to determine the safe live load on a bridge by comparing the capacity of each member to the force effects imposed by the demand of dead load, referred to as the weight of the bridge, and live load, referred to as the weight of vehicles traveling across the bridge. The rating is used to determine the posted weight limit expressed in tons. As shown in the figure to the right, the posted weight limit for the Fern Hollow Bridge was 26 tons. This limit was posted in 2014 following a load rating analysis in response to an inspector recommendation in the 2013 routine inspection report to perform an analysis of the structure's stability. NTSB investigators found 3 issues with the methods used in the 2014 load rating analysis. First, the thickness of the asphalt wearing surface was assumed to be 3 inches, consistent with the design plans. Post-collapse, the wearing surface thickness was measured to be about 6 inches as shown in the figure to the right. The doubled wearing surface thickness would have resulted in a load posting less than 26 tons if the thicker surface had been included in the load rating. Second, the load rating analysis assumed an incorrect K-factor for the bridge legs. A K-factor accounts for the degree of rotational restraint provided at a member's end. The load rating analysis assumed a K-factor that was only appropriate when the cross bracing for the legs was intact. Prior to the 2014 load rating, the 2013 routine inspection report indicated the cross bracing to the frame legs exhibited 100% section loss, as shown in the figure to the right. The retrofit cable bracing between the legs was not designed to provide lateral support, and the K-factor overestimated each leg's capacity. Third, the load rating analysis took the section loss at critical areas of the leg web, such as the inward facing of the southwest leg as shown in the figure to the right, and distributed the lost material over the entire length of the leg. In doing so, the load rating calculated a new equivalent web thickness for the legs as a whole, but failed to account for potential localized failures. Distributing the section loss over the entire leg length resulted in overestimating of the bridge's capacity. Staff found the calculations and assumptions used in the 2014 load rating analysis overestimated the Fern Hollow Bridge's capacity, and had the correct calculations and assumptions been used, the bridge would have been closed. Measuring accurate wearing surfaces on a bridge is important because it affects the estimation of the dead load, which in turn affects the load rating analysis. As mentioned previously, the actual asphalt thickness was nearly double the 3 inches specified in the design plan and assumed in the 2014 load rating. Except for the 2017 records, City of Pittsburgh paving records did not document how much asphalt was removed and replaced. Had the load rating engineer been aware of the thicker asphalt wearing surface in combination with other factors, the bridge's capacity would have been lowered. Staff found that the quality of the city's paving records was so poor that determinations could not be made about whether the actual asphalt wearing surface exceeded what was assumed in the design of the bridge, or about how long the thicker wearing surface had been in place. For this reason, one recommendation is proposed to the City of Pittsburgh to establish a system to ensure that its paving record-keeping practices are up to date. The most common technique to determine the thickness of an asphalt wearing surface is collecting core samples, as shown in the figure to the right. Coring is the process of removing cylindrical samples of material which is destructive, allowing water to enter the deck and damaging the asphalt wearing surface. Other commonly used methods include measuring the curb height and comparing the measurement to design plans, or to drive a nail into the asphalt and measure the visible part of the nail. These methods also have drawbacks, including differences in thicknesses across the bridge and the nail hitting aggregate providing a false measurement. A non-destructive method for assessing bridge decks includes ground penetrating radar, or GPR. GPR has been shown to be an effective method to assess the thickness of pavement layers, including asphalt, as shown in the portable GPR machine to the right. Some states are already investing in GPR as a means of moving away from coring. Guidance is needed on approaches to integrating GPR into common practice and promote greater use of the technology. Staff found that guidance is needed on the use of non-destructive techniques to verify the actual thickness of the bridge wearing surface. For this reason, one recommendation is proposed to the Federal Highway Administration to update the Bridge Inspector's Reference Manual, and one recommendation is proposed to the American Association of State Highway and Transportation Officials to update the Manual for Bridge Evaluation. I will now discuss the insufficient oversight by the agencies involved in performing and ensuring compliance with the Fern Hollow Bridge inspections. The City of Pittsburgh was responsible for inspecting and maintaining the Fern Hollow Bridge. Similar maintenance and repair recommendations were made in the inspection reports for more than 15 years leading up to the collapse, but the city failed to act on them, resulting in progressive corrosion to the point of failure. City records documenting work performed on the bridge was limited, and those that were available, such as paving records, provided little information. Following the bridge collapse, the City of Pittsburgh Department of Mobility and Infrastructure introduced several changes to its processes to improve management and oversight of city-owned bridges, including adding additional personnel and updating load rating analyses so that all vehicular bridges in the city have a current load rating. Staff found that the post-collapse actions completed by the City of Pittsburgh in response to the collapse of the Fern Hollow Bridge have the potential to address the deficiencies found in this investigation. For this reason, one recommendation is proposed to the City of Pittsburgh, and one recommendation is proposed to the Pennsylvania Department of Transportation to collaborate, and for PennDOT to take the lead in evaluating the effectiveness of the changes made by the city following the collapse of the Fern Hollow Bridge. PennDOT is responsible for ensuring that bridges in Pennsylvania are inspected in compliance with the National Bridge Inspection Standards, or NBIS. Although the Fern Hollow Bridge was inspected in a timely manner, the investigation of the collapse revealed that inspections were not performed in compliance with the NBIS. The Fern Hollow Bridge collapsed because maintenance and repair recommendations with priority codes 2 through 5 were not completed. Between 2005 and 2021, many maintenance and repair items were left unperformed, including reinforcing the stiffeners and repairing the rusted holes on all 4 legs, designated a priority code 2, and cleaning debris from the superstructure, designated a priority code 5. Post-collapse actions taken by PennDOT include updating its technical bulletin to ensure priority 2 maintenance needs are correctly classified and drainage systems are operating properly. PennDOT has taken steps to improve the inspection process and identify bridges in need of maintenance. However, it is critical not only that the maintenance and repair recommendations identified as priority 2 through 5 are appropriately coded, but action is taken in a timely manner to address the recommendations. Staff found that the post-collapse actions completed by PennDOT have the potential to identify at-risk bridges throughout the state. However, it is necessary to ensure that maintenance and repair recommendations are completed in a timely manner. Staff also found that PennDOT failed to provide sufficient oversight to the city of Pittsburgh. For this reason, one recommendation is proposed to the Pennsylvania Department of Transportation to develop and implement a plan to publish yearly aggregate data on bridge maintenance and repair recommendations. FHWA monitors the compliance of each state's bridge safety inspection programs by evaluating 23 metrics that correspond to the NBIS. To evaluate the metrics, the FHWA assigns a compliance level. There are 4 compliance levels: compliant, substantially compliant, non-compliant, and conditionally compliant. The specific measures and thresholds for each compliance level are identified in each metric. The selection of bridges is based on a random sample using FHWA's sampling tool. It is assumed that the sample of bridges is statistically representative of the overall population of bridges. FHWA uses a data-driven system to thoroughly investigate issues identified through these samples. There are more than 615,000 bridges listed in the National Bridge Inventory, or NBI database, of which 23,257 bridges are listed in Pennsylvania. Targeted data-driven reviews can be an efficient way for FHWA to investigate bridge safety issues such as those identified in the Fern Hollow Bridge investigation. Targeted data-driven reviews can include evaluating the need to conduct new load ratings of bridges with advanced deterioration and evaluating whether the assumptions and methods used in the load rating calculations are correct. Staff found data-driven reviews of targeted bridge populations to investigate specific bridge safety issues will help improve FHWA's oversight process. Once a problem is identified through the targeted review, FHWA can expand its review to address similar bridges to ensure the safety of those bridges for the traveling public. For this reason, one recommendation is proposed to the Federal Highway Administration to establish a process for conducting targeted reviews of the safety issues identified in this investigation. Sharing of lessons learned of the failures of the inspection program that contributed to the collapse of the Fern Hollow Bridge is important, so that similar bridge collapses do not occur in the future. Staff found the Fern Hollow Bridge collapse demonstrates the consequences of failures to complete inspections in accordance with standards, failure to correctly identify fracture critical members, failure to correctly perform a load rating analysis, and failure to respond to inspection findings and recommendations in a timely manner. For this reason, one recommendation is proposed to the Federal Highway Administration to incorporate the findings of the Fern Hollow Bridge collapse investigation into its bridge inspection training courses. This concludes staff's presentations, and we would be happy to answer any questions you may have.
Thank you all very much. I want to say I'm really impressed by all your work. I think I'm sure I speak for all the board members. You all did a phenomenal job, Dennis. I know that this was your first investigation from start to finish of a investigation at the board as investigator in charge. I know you took over for Skahari, but this was from start to finish. And I just want to tell you all, every single one of you, and there are lots of folks that were part of this, not just the three of you and Adrian and others, who really just did a phenomenal job on this. It's really impressive, the work you have done. So thank you. We are going to move into questions. I'm sure it's fair to say there are a lot of questions and issues we want to bring out a little bit more. I want to make sure that the board members can come on up. I think we're going to do this a little bit differently. The board members, if you want, we can all stay on. I mean, there's only 3 of us. If you want to turn your camera off, you are welcome to, but please, we can all stay on for the whole discussion. The first round of questions will be focused on the lack of action on maintenance recommendations. We will do as many rounds as you all have questions or we all have questions. I also want to provide for information purposes for those who are watching this. We're going to take a break after this discussion round. It's going to be a brief break just so staff can sort of adjust for the next 2 rounds of questions. It'll be about 10 minutes. And then we'll come back and do some questions on the ineffective bridge inspection program and on oversight or lack thereof of the insufficient bridge inspection program. Then we'll move into the board's findings or the proposed findings to the board, the proposed probable cause, the proposed recommendations, and then approval of the final report, during which anytime any member can offer amendments for consideration. So we will start with Member Graham with his questions and move on to Tom. And again, for you all, we'll do as many rounds as we need to make sure all questions are answered.
Right. Thank you, Chair Hamady. Good to see you this morning, both of you and Member Chapman. I too would like to commend the team for a very thorough and quick investigation. And the report is excellent, and I really appreciate that. So let me start by what year did an inspection report first note holes or 100% section loss in the transverse stiffeners of the Fern Hollow Bridge? You're muted.
Sorry about that. Someone had to do it. So the earliest inspection report that investigators reviewed was the 2005 inspection. And in that report already, there was 100% section loss noted in the transverse stiffeners.
Yeah, I'm reading here from that actual report. It says the transverse stiffeners attached to the near right frame leg exhibit several areas of up to 2-inch by 4-inch of 100% section loss, and other transverse stiffeners on all frame legs exhibit similar severe corrosion with up to 75% section loss. Can we pull up photo 17 of the 2007 inspection report on page 34? I think you guys have that loaded up. Yeah. The 2007 inspection report also identified worsening corrosion and 100% section loss. Can you please discuss the recommended repair?
Sure. A repair such as this would typically consist of first cleaning the rust and debris from the immediate area. and followed by the installation of additional steel plates, either on one or both sides of the existing stiffener. And then those would either be bolted or welded in place, depending on the condition of the existing stiffener and what it could support.
Thank you. Do you know what code was assigned to that recommended repair?
That would have been a priority code 2.
Priority code 2. Was that completed, that repair?
No, we were not able to locate any evidence that those repairs were made.
Okay. Can you now pull up photo 61 of the 2013 maintenance report? That's from page 45. So, continued neglect of the Fern Hollow Bridge from 2007 to 2013 led to section loss on the near right leg to grow to, and this is out of the report, 11-inch by 11-inch hole. The 2013 report again recommended to repair or replace the stiffeners and web on all 4 legs with a priority code 2. How is it that despite the significant corrosion and section loss that occurred from 2007 to 2013, the priority for that repair was still a code 2? Would you say that's an appropriate code for that recommendation? The 2?
So, I mean, this can be a difficult question to answer without having been there at the time the inspection was conducted. However, working from the information that was documented in the reports and what the inspectors had at the time, which included the fracture critical member identification framing plan that I discussed earlier, and the fact that the legs were not identified as fracture critical members, the maintenance priority code of 2 really would have been a reasonable code, given the fact that the repair recommendations should have been made by the owner within the 2-year period before the next inspection. Now, had the frame legs been properly identified, as I discussed earlier, as FCMs, the maintenance recommendation should have been given a priority code of 0, which would have required immediate action, which is one of the reasons why staff is proposing that the bridge owners be required to conduct a one-time review of the existing FCM plans to make sure that all FCMs are properly identified.
Okay. Can you pull up page 50 of the 2021 inspection report, please? In another picture. The last inspection prior to the collapse was on September 29th, 2021, about 4 months prior to the collapse. The section loss had now grown to 12 inches by 12 inches, as you can see. Did the September 21 inspection report recommend any immediate action?
The September 2021 inspection report did recommend that the holes and section loss be repaired, but again, it was coded as priority code 2, so it would not have been required as an immediate action item.
Thank you for that. I see my time's up, so back to you, Chair.
Thank you. And we'll come back again. Really great questions. I think these are really important issues that we get into. So thank you, Member Graham. Member Chapman. Oh boy. I hope there's not a fire alarm. We're going to, if there is, I'll come back and talk about that for a second, but go ahead.
Thank you, Chair. Here in my kitchen in Bethesda, we are having no fire alarms. So I want to.
Tom gets to take over. We'll come back by mobile phone. No, I'm just kidding. Go ahead.
I want to join my colleagues on the board in commending all of you for really outstanding work. I'm always so impressed by what our team does with regard to all of these investigations, but this one I think is particularly impressive. The piecing this together and trying to determine what happened was quite a task, and you are to be commended for outstanding work. The draft report indicates that PennDOT contracted to have something called a finite element model developed, and I know this was covered in the staff presentation, but I just want to come back to this a little bit. A finite element model was developed to evaluate the original design of the bridge and to examine the collapse sequence. Can you just discuss again what is a finite element model and what is the purpose?
A finite element model is a way of examining a complex structure by breaking it down into smaller pieces. Essentially, you take a large complex design and discretize it, and you examine or analyze however you want across each one of those small blocks. And then you can therefore look at either local effects or effects of the model as a whole. It's kind of like if you built the bridge out of Legos and then analyzed each individual Lego block and then sum those all together so you can look at the behavior of the overall bridge.
Thank you for that. And I believe I'm correct in saying that the model suggested that the bridge had sufficient capacity as originally designed had there been no section loss due to corrosion. Is that right?
That is correct.
Our draft investigative report summarizes inspection findings and recommendations made between 2005 through 2021. Am I correct that clogged drainage inlets were first documented in 2005?
I will defer to Mr. Collins on that.
Mr. Prouty has that data in front of him, is double checking, but I believe they were documented that far back.
Yeah, they were documented in 2005, but again, 2005 was the earliest report that we had reviewed, so.
Okay. And at that time, corrosion of the southwest leg was already evident, correct?
Correct.
After 2005, it's my understanding the clogged drainage was only cleared once. That was in 2009, at least so far as we know. And no work was done to repair or reinforce the section loss in the bridge legs. Is that also correct?
Correct.
Now, considering the lack of patina, which resulted from as I understand, from the corrosion and the poor drainage, what else should or could have been done to stop the progression of destructive corrosion?
Certainly one of the easier things that could have been done would have been to apply a protective coating, such as paint or an epoxy type coating.
Now, had proper and timely inspection and maintenance been conducted, could the Fern Hollow Bridge have continued to carry the designed load indefinitely? In other words, is there a life expectancy for a bridge such as this?
There are life expectancies for bridges. They're based on a multitude of factors, not just their structural integrity and not just the integrity of the bridge, not what the condition of the bridge, but also other factors such as, is it still suitable for the proposed traffic volumes that need to cross it? So, but just focusing on the structural capabilities of the bridge, had it been properly maintained and things had been repaired properly and the rust had been prevented from getting worse, then it certainly would be expected to last many more years. We examined a very similar bridge, made of the same materials, the same design, right around the same time, within a year or two of this bridge in West Virginia. And that bridge is in very good condition, and we would expect that bridge to keep going as long as it's maintained and still be quite functional for many decades to come.
So the bottom line is, with proper maintenance, this bridge should have been nowhere near its useful life, at least structurally.
Correct.
Thank you, Chair. I'll save my questions.
Thank you very much. Please start my time. So following up on that question from Member Chapman, how many uncoated weathering steel bridges are there in the United States?
believe there's just over 10,000.
And because and the reason I asked this question is really where Member Chapman was also going, because we will get a question of what is this material that is safe to use in bridges? Are these bridges safe? Should the design be changed or the materials changed? And just repeat what you just said, because it was essentially exactly what I was looking for, because that will be, I'm sure, reported later. Go ahead.
So again, there's just over 10,000 bridges made in the United States made of uncoated weathering steel. Had that bridge or any bridge made of this material, or any bridge made of any material for that matter, as long as it's maintained and is not outliving its ability to handle the traffic volumes that are being asked of it, those bridges will continue to function properly. This was not a matter of the uncoated weathering steel being used as the material. Had it been maintained properly, there would not have been a problem. Given, like I gave the example of the very similar bridge in the neighboring state of West Virginia is still doing very well.
Great, thank you very much. This gets into the discussion on inspections, but and I'll get into some of this more in the next round, but was the city alerted to the poor condition of the bridge and the conditions that led to its deterioration?
Yes. Every time the bridge was inspected, an inspection report was provided to the city as the owner. And so they were, like you said, all these things were called out year after year as being problems. Recommendations were made as to what needed to be done to fix them year after year. And those items were just never taken care of.
And at some point, there was a rehabilitation plan for the bridge or for bridges in general. Can you talk about that a little bit?
The rehabilitation plan that was specific to the Fern Hollow Bridge was drawn up, I believe, in 2008, and work was then performed in early 2009. So some rehabilitation work was done. There were several items on that on the list of recommendations from the consulting firm that put the plan together. One was to replace the cross braces because of their condition. Another was to apply a rust inhibited coating to the bottoms of the legs and the end of the main girders, places where corrosion had been noted. They also, during that evaluation, noticed that the bridge didn't have as much lateral support for wind loading that it should have, which is the reason why the cable braces, the retrofit cable braces, were installed. And then they also recommended replacing the downspout system, which had in a lot of places rusted through and was leaking what was getting through the drains down onto the legs. So those were the things that were proposed, and the only things that were actually done was the replacing of the downspout system, which as a result required cleaning of the drains, and then the addition of the cable bracing.
Great. I'm going to ask you to just respond to this quote. The bridge engineer indicated that local communities don't do bridge maintenance because they don't have the money, that they have to have enough things wrong with a bridge to then have a project that can be funded with capital funding effectively. Do you have a response to that?
I'm going to defer to Mr. Collins for that.
I think staff and the board would recognize that all localities have priorities. We would expect that particularly repeated problems, such as identified here on this bridge, should continue to get attention and move up in the priority list. We do think that there's a safety component to that system that should have kicked in, but as described in the presentations, things like the improper FCM plan and identification of the members caused it to not. So our recommendations are aimed at improving that side of it. So we hope if the board considers and adopts them that we can prevent this sort of thing from occurring in the future, despite all localities facing such concerns.
It's absolutely critical to ensuring safety. Okay, we're going to go to Member Graham, but just really quickly, there is a fire alarm test in the building. We have been in communication with the building's engineers. They are fine. It's just a test of the system. And so we're just going to continue on while they do the test, but everybody has been alerted and we've been in discussion to make sure everybody is safe. So with that, Member Graham.
Thank you. They have some very long fire drills, don't they? I'm going to go back to what I was talking about when I first started. I was trying to basically show the documentation from 2005 up to 2021 that section loss started in the transverse stiffeners from about a 2 inch by 4 inch all the way up to 12 inch by 12 inch. And if I'm right, I don't think those were ever coated less than a 2 for a priority. Is that correct?
That is correct, yes.
So let me ask you, what does it take to get a 1 or a 0, a critical or a high priority to be repaired or replaced?
Again, that essentially is a judgment call by the inspectors. Just trying to look at the PennDOT classifications, but they certainly could have dropped at least to a 1. In our opinion, they probably, having spoken with the inspectors and during the interviews and stuff, they were really kind of relying on the fact that those were not identified as fracture critical members, which is why that they didn't drop them below the 2.
Okay.
And they actually did mention that had those been identified as fracture critical, then they would have assigned it the priority code 0.
Which is very interesting you say that, because I'm going back, I'm looking at all the reports from 2005 to 2021. Only 4 maintenance and repair items were coded a priority 0, none of which addressed the corrosion on the bridge legs. I thought it was really interesting that 2 of them that were coded 0 were the load posting signage, which doesn't seem that. Yeah, there were 2 that were coded 0 to get it correct, I guess. The loading sign, which really doesn't affect the ability of the bridge to stand up, at least by itself. Another one there was removal of a corroded light pole. What does that have to do with holding up the structure of the bridge?
It wouldn't have anything to do with holding up the structure of the bridge. I assume that it was assigned to priority code 0 just for safety concerns of it falling into traffic or onto traffic.
Yeah. There was only one for the removal of the corroded cross brace that began to fall off the bridge. So I think it's just interesting that maybe they lost their priorities or didn't understand their priorities when it came to their bridge inspections. But because, this bridge didn't collapse just by an act of God. It collapsed because of a lack of maintenance and repair. And that's just sad for the city. Let me move to the cross bracing. I believe there was a rehabilitation project planned for 2009 to replace that. Is that correct?
That's one of the items that was proposed to be completed with that rehab project.
Yeah, but they ended up putting in steel cables instead.
Correct.
So what is the difference in loads that a cross brace can handle compared to steel cables?
Well, the cross bracing, the rigid cross bracing can handle both compressive and tensile forces, whereas just the cable bracing can only handle tensile forces.
Yeah. So just putting up the steel cables really doesn't solve the problem of replacing the cross brace. Is that correct?
That's correct. Like
Go ahead.
Like I mentioned earlier, the retrofit cables were intended to be a temporary measure, and then to supplement the lateral loading from wind forces. But the original plan or proposed recommendations for that rehab was to replace the rigid cross members in kind.
Yeah, because some of those cross braces had a complete 100% loss at the bracing, if I remember right, that you put in the presentation. Do we know if any of the cross bracing was ever removed?
The lower cross bracing on what would be the west end of the bridge was removed. And I think that was in early 2019 that was removed.
Yeah.
And it was essentially falling off the bridge, and there was concern it was going to fall onto the trail below and possibly hit hikers that were on the trail. So it was ultimately removed.
Exactly. And do we know what action was taken to have that cross bracing removed? Was it the city doing it, or was it a posting on social media by a concerned resident that walks under that bridge every day that got the attention, and finally a few weeks later that they came out and removed it? Is that correct?
The timing of that social media posting and the removal certainly suggests that the social media posting played a role in the increased awareness of that risk and its mitigation.
Sure sounded like it to me too. Thank you for that. And I'm out of time.
Thank you, Member Chapman.
Thank you, Chair. I believe I'm correct that in 2011, the superstructure condition rating for the bridge dropped to 4, which is a poor condition rating. And it remained at a 4 through the 2021 inspection reports, which I think was 4 months or so before the bridge collapsed. How is this rating determined, and what does it mean for a bridge to be rated as in poor condition?
So a bridge rating of poor is described as. Can you pull up slide? I believe it's 110. But ultimately, a poor there it is. A poor rating is going to have advanced section loss and deterioration. And then the spalling or scour that's also listed on there is referring to the concrete, typically in substructure.
Okay, and when we say poor condition, does that necessarily mean unsafe condition, or is that kind of a site-specific determination?
I wouldn't say that it necessarily means an unsafe condition. It's looking at the entirety of that item, which in this case is the superstructure. And I guess so how those ratings are given is that the inspectors they need to assign a condition rating to each of the main elements of a bridge. So the deck, the superstructure, substructure, and then if there's any culverts or scour protection, that type of thing. So each of those main elements would get a rating on its own. So the rating of the superstructure in this case, if you think of it like grading or rating a bunch of bananas, you may have a bunch of bananas where most of them are in really good condition, but you might have one that's getting too ripe and turning brown. So you would take that into account, but you wouldn't downgrade the entire bunch just based on that one banana that being overripe.
Once a bridge is rated as in poor condition, it doesn't mean that it's unsafe, but certainly as a practical matter, it means that some additional scrutiny or attention is warranted.
Member Chapman, if I could answer that question.
Sure.
Yeah, absolutely. The superstructure was rated a poor condition, which is advanced deterioration and section loss. FHWA post-collapse did look at these condition ratings and determined that the superstructure should have been rated at a minimum condition 3, which is a serious condition. That would a serious condition has potential localized failures, which this bridge did, and could have been rated as a condition 2, a critical condition, in which the bridge may be necessary to be would be necessary for closure until corrective action is taken.
So once this bridge was rated as a 4, not only should it have been subject to some scrutiny, but apparently even additional scrutiny didn't result in it being properly rated, which is really at a lower condition than poor condition.
That's
right?
Correct.
Yeah.
Correct.
Do we know what percentage of bridges in the U.S. have a poor condition rating?
Member Chapman, of the 615,000 bridges that are in the National Bridge Inventory, approximately 43,000 bridges are rated in poor condition, or 7%.
Okay, thank you very much. Chair, I have one last question. I'll just save that for the next round.
Thank you. And I just want to emphasize that this round is on the maintenance. For the inspection round, that is the second round that we're going to get into. So do we have any other questions on the maintenance that was or really was not performed on this particular bridge?
My question.
Graham?
Yeah, I do have some too.
Great, go ahead.
Oh, okay. I appreciate the discussion a little while ago about, the where communities put their money and how it's used and stuff like that. But I just thought it was really interesting that you all point out in the report that basically last year from August 2022 to July 2023, the city of Pittsburgh spent $1.267 million on bridge inspection, maintenance, and repair. And that amount was, I think, quadrupled from the 4 years prior, from 2018 to 2021, which was $1.199 million. How many bridges does Pittsburgh own and maintain?
Dr. Sweeney, do you have that number? I'm afraid I don't have it, the total number of bridges in front of me.
Sure, I believe it's about 280 bridges in Pittsburgh that are in the National Bridge Inventory. They may have more that.
Yeah, well, there's the
that.
Allegheny County, but I saw that they own 147. They maintain 147. That number may vary, but if you look at the money of that, for that 4-year period prior to last year, they were spending roughly $300,000 a year to maintain and repair their bridges at 147. That if you give dollars to every bridge, that's roughly just over $2,000 per bridge. That doesn't seem like very much for an area that is known for corrosion and rust. And even last year's money, if you add it up, it's only about $8,600 per bridge. Does that seem like enough to keep a large number of bridges going in this area?
Thank you for the question, Member Graham. It's important to remember that the monies are generally prioritized. So in a given year, you may have a lesser maintenance need for a particular bridge and a greater maintenance need for another. So the amount of money, I think, isn't specifically the problem. The issue lies really at its heart with the prioritization, specifically having the good data from the inspection reports, the proper data in terms of the FCMs to allow you to properly apply the limited resource that is funding. And I will say that we were in communication with the city, and that since the collapse, they have done a survey of all the bridges. They have created, with the help of an external consultant, some prioritizing of that list, and they are applying that money specifically for maintenance to both prevent future damage and correct current damage. So again, I don't want to comment on the specific amounts, but simply to say that, as we found in the report, it's the good data in to let you make good decisions, and we're hoping the recommendations that we proposed will address that.
Thank you for that, Mr. Collins. That's all I have in this section, Chair. Thank you.
Thank you, Member Chapman.
Chair, I have one more question that I prepared for this round, but I actually think it will fit better in our next round, so I'm going to save it.
Okay, great. We are going to take a 10-minute break. We will return, well, a little bit more, 13-minute break. We'll return at 11:25, and then we will move through the rest of the two sections and the findings, probable cause, recommendations, and consideration of the report. So with that, I will remind everyone to turn off your mics and turn off your cameras. Carl, I think we're going to go ahead and return from break. Okay, great. We are now going to move into our second round of questions on the ineffective bridge inspection program. I just want to remind everyone that when it comes to the authorities of federal highways, the state and the city and their oversight, that is in the third round. So with that, I will turn to Member Graham.
Thank you, Chair. All right. I know we discussed how the inspection reports identified significant section loss in the legs, but when inspecting a bridge, the section loss only tells part of the story. It's also important to thoroughly measure and document the thickness of the remaining sections. Can you please tell us why and the consequences for?
Sure. The main reason that it's so important to document the thickness in the remaining material is so that the load rating calculations, which are conducted based on the information from those inspection reports, can produce as accurate of a load rating as possible. I guess the old adage of garbage in equals garbage out really applies here. The better information you have to put into the load rating calculations, the better and more accurate the results are going to be, which is one of the reasons why staff is recommending that this collapse be used as a case study in future inspection training courses to reinforce how important it is for inspections to be conducted properly and documented thoroughly.
Okay. Can you please explain further how corrosion can lead to incorrect measurements of the section loss of the remaining sections?
Sure. Can we have slide 19 pulled back up? As we saw during Ms. Lamb's presentation on the corrosion, that corrosion can build up. The specific portion of the slide I'm looking at here is the upper right-hand corner, the lamellar corrosion. So if you were to take a measurement of that area there, you can see that the multiple layers of corrosion built up on the actual steel that's in the middle of there. If you were to take a measurement of that, it would significantly over exaggerate the amount of remaining steel that's actually there. And then if that thickness were to be put into the load rating calculations, for example, you would get an overestimation of the capacity that would have. So cleaning all that rust away down to whatever little portion of that good steel was remaining would give you the most accurate results in the load rating calculations.
Were the inspectors prior to the bridge collapse and all those years of inspection up from like 2005, were they cleaning those areas before they measured?
It's hard to tell just from the photos, but there's little evidence that there was much of any cleaning being done. There weren't, I don't recall any photographs showing it. It doesn't mean that photographs were taken and then things were cleaned, which could have been the case in some of the instances. But just one of the things we noticed was rather than actual measurements of how much steel was left, it was basically like a guesstimate. 50% of it's remaining, instead of providing good, accurate measurements that could have been used by the load raters.
Has anything changed with the inspection program since this bridge collapse? Or for the cases of measurement and all?
We don't have any evidence or knowledge of what's currently going on with inspections. However, we do have knowledge that the Federal Highway Administration has been planning and was planning prior to the collapse of this bridge to update their fracture critical member inspection training course. So because they're in the phase of being able to revamp that program, and because they were parties to the investigation and have had a lot of this information early, they're able to start rolling that information into their new training course to help emphasize the importance of these measurements.
Okay, thank you for that, Mr. Prouty. I see my time is up. Back to you, Chair.
Dennis, can I just for a second, Dennis, I think you wanted to add to that, so go ahead and then we'll turn to questions from Member Chapman.
Thank you. The only thing I would add to Mr. Prouty's answer is that another component would be one of the recommendations staff has proposed to Federal Highway to use this collapse as a lessons learned. It will give them although cleaning is already covered in the training materials, emphasizing that issue in the context of Fern Hollow will give it more weight to all of the bridge inspectors across the country as they get trained and go through recurrent training. So we also think, in addition to Federal Highways changing, that additional change that we proposed as a recommendation should also help.
Thank you.
Member Chapman.
Thank you, Chair. The posted load limit for the bridge was 26 tons, but an accurate load rating analysis using correct calculations and assumptions apparently would have reduced the estimated load posting to approximately 3 tons or 6,000 pounds. And that is, according to my calculations, only 12%, about 12% of the posted load limit. Am I correct that a load posting of 6,000 pounds should have warranted a closure of the bridge?
That's correct, Member Chapman. The bridge rating guidelines indicate that a posted weight limit of 3 tons is a criteria for the bridge to be closed.
And now I'm going to wander into areas that are well outside my comfort zone in terms of the concepts and terminology. I think this was mentioned in the staff presentations, but can you repeat, please? What is K factor, and what is the significance of K factor in determining the load rating of a bridge?
Thank you, Member Chapman. The K factor is the degree of rotational restraint around a member's end. And as indicated in our presentation, in the 2013 routine inspection report, the member's end was exhibited 100% section loss. So it was not intact. The 2014 load rating assumed a K factor that was 0.75, which is a factor used when the member's end is intact. And so post-collapse, FHWA determined that the conservative factor that should have been used in this case was a K factor of 1.2 to 1.4. And in fact, if that K factor had been used, the bridges over the overcapacity of the bridge legs would not have it would not have been it would have been correctly assessed as part of the 2014 load rating.
Thank you. That's helpful. Now, I believe that the finite element modeling, which was discussed earlier, that the results from that modeling, and I'm quoting from our draft report, the results indicated that the extensive section loss played a much larger part in reducing the modeled bridge's ability to carry loads than the additional weight of the wearing surface thickness. So with that in mind, are we able to say, as between the incorrect K factor, which you just discussed, and the faulty section loss assumption, do we know which of those two variables might have most contributed to the incorrect load calculation in 2014? Do you follow that?
I do, and thank you for the question. Staff believes the most contributing factor to the incorrect load rating was the section loss.
Section loss, okay.
Correct. Now, there were other two contributory factors associated with that. Was the incorrect assumption of the K factor,
okay, and
also was the incorrect assumption of the asphalt wearing surface. The 2014 load rating used 3 inches of asphalt wearing surface. It should have used 6 inches.
So all of those were factors, but the section loss was the most significant.
That's correct.
Okay, thank you. Do we know how many bridges with non-redundant steel frame leg designs are identified in the National Bridge Inventory, or approximately? And if not, we can talk about that later, but I'm just curious if we happen to know that number.
So the type of bridge again is non-redundant steel frame.
Yeah, non-redundant steel frame leg designs. Do we have a sense of how many bridges in the National Bridge Inventory might be of that design?
I believe we do. If I remember correctly, that would have been the targeted population from the interim recommendation. So I want to say that was around 10,000 bridges.
Okay.
And Mr. Collins or Ms. Sweeney or Dr. Sweeney can clarify that if I misspoke.
Let me take a shot at that one for a minute, Steve. There are, as Steve mentioned, as Mr. Prouty mentioned, there are about 10,000 uncoated weathering steel bridges in the country. Of those, we think there are approximately, that's uncoated weathering steel. There are more steel bridges in our country, and of those, that larger sample of steel bridges, there are about 270 steel bridges with a frame design. What we don't know, however, if those are all non-redundant. That's not to say we can't.
Okay, thank you. And I'm sorry, I didn't mean to spring that question on you. But I appreciate the effort to try to respond. I will come back to my remaining questions. Thank you, Chair.
Thank you. So the city could do their own inspections. They contracted with a PennDOT contractor. Can you talk about, so the PennDOT contractor, are they hired by PennDOT? And then the city looks at a list and says, that's a good contractor. Do they ask PennDOT for, a suggested list, or what is the process there?
So I know that I can answer part of the question. So I know that essentially PennDOT has contracts with multiple consulting firms, engineering consulting firms that have people that are trained and certified to do bridge inspections. I don't know exactly how they're selected for each particular investigation or inspection rather. But I do know that essentially there's a pool of ones that are already set up with PennDOT. They have contracts in place to go out and do these bridges. I believe that the city essentially tells PennDOT that it wants them to take care of inspecting those bridges for them, and take care of the logistics of that. And then I don't know what the internal selection process is as to how they're assigned to which consulting firm.
Oh, the city says we could do our own inspections, or we reach out to PennDOT. They reached out to PennDOT and said, we want you to do the inspections. PennDOT has a number of contractors, and PennDOT chooses the contractor. Is that right?
Again, that's the part that I don't know exactly how
Dennis?
they're chosen or assigned.
I believe that the contracts cover either the districts for PennDOT or particular parts of Pennsylvania. So a particular contract will be awarded to a particular firm to cover a particular area, say Allegheny County or District 11, or maybe even 2 districts. But that's all handled on the contracting end, and that's awarded through the contracting process by PennDOT. And then, as you said, the rest is true. The city says, hey, we're not able to do our own inspections. We don't want to do our own inspections. We'd like to use your contract vehicle. And that reduces some of the funding from a particular source they get from PennDOT. That's how it's paid for. And then the inspections are scheduled according to their inspection interval for a particular bridge and executed under the PennDOT contract.
Okay, and so PennDOT what I'm hearing is PennDOT has somebody for that area, that district.
Yes.
That they've contracted with. Okay. So, I'm not going to get into the oversight portion of this. I'm going to wait. That's the next round of questions. But how are the contractors screened? We had a number of situations here where, you had fracture critical members that weren't identified. You had an engineer say that it was in compression and not tension. You had another one say, you had a number of them who did not remove corrosion or clean the area prior to inspections. I'm just wondering, how do they verify that they're trained?
All of the bridge inspectors are required to undergo training that's overseen by Federal Highway Administration. They're also required to meet some specific requirements for the state of Pennsylvania from PennDOT. So when the contracts are bid, they have to, the contracting company has to certify that they have appropriately qualified personnel that meet those requirements. So in effect, PennDOT and the city are relying on the Federal Highway certification and training of the inspectors As this case demonstrates, there was clearly a disconnect between what's being offered in the training and what's being applied in the field, which is where the recommendations that we proposed to Federal Highway related to their training come into effect.
And I'm out of time, but I'm just going to ask one question. Was it one contractor the entire time or different contractors?
With respect to the Fern Hollow Bridge, which is the only one we looked at in this level of detail, it was, I believe, 4 different companies. Mr. Prouty or Ms. Sweeney might be able to correct me on the number, but it was several different contractors over the time period we looked at from 05 to 21.
So I'm looking at this that's here. So from 2005 to 2021, there were 3 different named engineering firms. However, between the 2013 and 2014 inspections, the firm that was doing the inspections from 2005 to 2013 merged with another engineering firm. There was a name change, and then essentially the same personnel and company carried on then through 2019, and then a totally separate engineering firm started inspecting them in 2020 for the 2020 and 2021 inspections.
So 2 or 3, essentially.
Yes.
Okay. All right. I've run out of time. I have more questions on that, but Member Graham.
Thank you, Chair. So of all those different inspectors over that time from 2005, none of them were able to identify the legs as fracture critical members?
None of them did.
None of them did. Yeah. Wow, that's just amazing. Has anything changed in the program of these inspectors for training or anything to be able to identify fracture critical members?
We do know that in the reworking of the FHWA's fracture critical training program, that they are putting more emphasis on the identification of fracture critical members. And that's also, again, why we've made the recommendation or proposing the recommendation for additional guidance. When you have areas that are typically considered to be in compression, such as legs or columns, would normally be considered to be in compression. But as we saw, there are definitely areas sometimes, especially when you have angled legs, that will require, or that do have tension within what normally would be considered a compression area, which is why we're asking that additional guidance be provided in the berm and MBE, as well as what's already being placed into the FHWA's updated training course.
Okay. Who is in the best position to determine fracture critical member, or what we're called now, I guess, is a non-redundant steel tension member? Who's the best person to do that, to determine that?
The best person to do that would be in the very beginning of the bridge's life cycle, or the life, which would be in the design stage. So the person that's designing the engineer and is already designing the bridge, they're already conducting all the calculations, running the computer models and everything. They would know where the areas of tension are.
It sure would seem smart if that kind of information is provided to the owner or the inspectors. Has any of that changed over all these years?
Yes, it definitely has changed. I know starting, and I think it was around the late 70s, I would say 78, that there was additional, there were changes in that. Yeah, so in 1978, there was the first publication of the fracture control plan, and that was published by AASHTO, and it is now included in the LRFD bridge design specifications, that it's actually a requirement now, and it went fully into effect probably early to mid 80s. But since that time, fracture critical members are specified in the design stage, identified in the design stage, and that information is then passed on to the fabricators who build the bridge and build the components to assemble the bridge, so that they actually use different materials when necessary. They aren't necessarily making the bridge stronger, but they're making it more resistant to fatigue and fracture. Basically using materials that will bend or give rather than just break without warning. And then so that there's some warning there. And then that from the fabricator, then that information is passed on. It's included in the design plans all the way through, so that inspectors then basically have, since the 80s, have plans now that come to them with that fracture critical members essentially identified. So the reason we're asking or proposing the one-time review is to catch all the fracture critical plans and the bridge designs that would have been out there prior to this these new processes, to make sure that everything has been caught on the older bridges, and the newer bridges should be taken care of.
Very good. That's a good answer. I like that. Thank you. That's all I got in this section, Chair. Thank you.
Thank you, Member Chapman.
Thank you, Chair. Just a couple of questions from me. Mr. Prouty, you referenced the recommendations that we'll be considering later on today. Those are draft recommendations 2 and 10, and they call on FHWA and AASHTO respectively to develop guidance which addresses the identification of localized tension zones and tension components in non-redundant steel members. It sounds like maybe they're moving in that direction, or at least FHWA might be moving in that direction already, at least based on what you said with regard to some of what they're doing with their training. Have we had any discussions with those agencies? Do we have any sense of how long it might take these entities to develop and distribute that sort of guidance?
Typically, to make changes to the guidance like this, it would take anywhere from 5 to 7, maybe 10 years to get that in place, which is one of the reasons that we are also proposing to get that information out sooner, is to get it into the training program that FHWA provides for bridge inspections. And that way it will get out much sooner to inspectors all across the country, as opposed to just addressing it locally, say in Pennsylvania, and also faster than it can get through the other process to update the guidance.
Yeah, that's interesting. I didn't realize that we were potentially looking at that kind of lead time. So certainly, I hope folks will work hard to get that out as quickly as possible. And I recognize it takes time to develop, particularly when you're talking about some technical concepts. It takes time to develop these things, but there's clearly a need to get that out as quickly as possible in a useful fashion. Mr. Collins, did you have something you wanted to add?
Thank you, Member Chapman. Yes, I'm able to provide a little bit of clarity. We did have some very recent communication with AASHTO, and they were able to confirm that using their process with things going through committee and then being brought to the entire organization for voting, their time frame would be about 5 years. Okay. In order to get that all the way through. However, fortuitously, they are right now ramping up to begin that cycle process of changing their documentation. So it appears that we're making a very timely recommendation to AASHTO.
Well, that's good. But it's on the radar, sounds like.
It is.
Good. In July of last year, I understand that Federal Highway Administration issued a memorandum to bridge owners in response to our recommendation at the time. And our recommendation called on FHWA to develop a risk-based, data-driven process to help bridge owners identify, prioritize, and perform follow-up actions documented in inspections of bridges with uncoated weathering steel components. It's encouraging that they moved as quickly as they did. Do we have a sense of what bridge owning agencies are doing to implement the FHWA developed process, or is it too early for us to be able to assess that?
We do. So in July, the FHWA sent their memo out to state departments of transportation and other bridge owners, asking them to identify their uncoated weathering steel bridges, and within that, divide them into basically two categories: those that had condition ratings for superstructure or substructure rating of 4, or element rating of 4 as well, and the other group, those that did not, fell into the other group. For those that had that poor condition rating, they have reported that those numbers back to FHWA. It's about 367 bridges that they're looking at across the country. The second part of the program is for those state departments and those bridge owners to ensure that the maintenance and recommended repairs are completed, and that the load ratings are verified for those bridges, that they're done, that they're accurate, and report those numbers back to the progress on that work back to Federal Highway by the end of 2024. For the other bridges that did not fall into that category, they are also to be looked at for maintenance and ensure that maintenance is completed, and to assess those load ratings, and that would be done within the next routine inspection level.
So that's encouraging. So the process that we recommended has been put into place, it's being implemented, and it sounds like, at least at this early stage, is starting to yield results.
Yes, sir.
Yeah, that's encouraging. Chair, that's all I have for this section. Thank you.
Okay, thank you. And I'll check back. I have some questions. So I'm just looking at the draft report. The manual for bridge evaluation requires a written and documented inspection plan for fracture critical member inspections, underwater inspections, and inspections of bridges with complex features. Before 2011, how were the FCMs or fracture critical members documented?
So
it says hand-drawn figures with notes.
yeah.
So what was available to the inspectors at that time?
So there are essentially 3 different stages that we kind of called out in the report. Prior to 2011, it was hand-drawn figures and notes that were taken and incorporated into the inspection report, which would then be passed on to the next either crew or next firm that were to do the inspection. They always have available to them prior inspections, especially the most recent prior inspection.
Let me stop you right there, because I think you're going to go then to 2013 or 2015. So the prior to 2011, those hand-drawn notes, was it did it come from an engineering firm that had determined the fracture critical members prior to that, or was this something the inspectors provided? Where did that information come from?
Some of the hand-drawn figures were from before 2005 when we started looking at the inspection reports, so it's hard to tell exactly where they came in, but it did appear as though some were added along the way. So they're being added as inspections were occurring, and as it was important to help document some of the different things that they were finding.
Okay. So then there is a fracture critical identification framing plan, a diagram at some point developed by an engineering firm contracted by PennDOT on behalf of the city sometime after 2011, I think 2013. And then there was another one in 2016, also a different engineering firm, also contracted by PennDOT with a fracture bridge inspection plan that included a new fracture critical identification framing plan. Did either one of those correctly label the fracture critical members?
No, they did not.
Why? Did they have the information at the time? Should they have?
Again, as I talked about in my presentation, the information was available on there was information available on the design plans for the bridge that should, at a minimum, have got them thinking that their bending stresses and bending moments can be transferred into these legs. There should be, some additional structural evaluation done or analysis done to determine whether or not there were any parts of those legs in tension. And again, also looking at the geometry, as we showed in the animation, and I briefly talked about in the presentation, is that where the sharp bend near the bottom of the leg in the shoe region, that caused there to be tension induced in that area, which was carried by the transverse tie plate.
Yep. And so what I'm trying to get at is the inspectors themselves. So the fracture critical member identification was done by some engineering firms contracted by PennDOT. For the inspections, which occurred at certain intervals every 2 years, sometimes annually, the inspectors themselves, they used the information provided in these diagrams, correct?
Correct.
Could an inspector have evaluated the bridge and come up with said, hey, there's something wrong with this diagram? Or is that something the engineering firm does? And is it typical that an inspector would rely on that documentation to do their inspection?
Certainly, it would be within the inspector's purview to question what's there, and either ask questions or a request that it be reevaluated.
Sure. So how often does
inspectors-
that happen, or do they usually just rely on the documentation that was already provided by an engineering firm hired by the person who you have a contract with?
It'd be difficult to say for all bridges, but for the Fern Hollow Bridge, it was evident that they essentially were just going with the plans that were there.
Who is the same contractor have the contract now with the new bridge for inspections?
We're not aware of which firm has been tasked with inspecting the new bridge.
And do you know if did have the inspections, and I think Member Graham asked this, but have the inspections changed at all, the process? I understand that you talked about training, but beyond training, there's training and what you could get in a training course. And, in this situation, you had just mentioned that what's in the documents and what some here didn't sort of line up, but you provide the training, and this sort of starts to get into the next section, so I'm not going to go too deep into this, but is there a new inspection process? Is there, does PennDOT have a new way of thoroughly evaluating what their contractors are doing, and have they developed a new inspection plan?
PennDOT has updated its publication 238, which is what its inspection manual is for use out in the field. They have created a whole appendix focused on uncoated weathering steel, which should be released towards the end of this week or early next week. We also know that they are in the process of developing a load rating guidance for their inspectors as well, to use. They have changed a little bit their quality control and quality assurance programs. They're looking more in depth at those bridges with condition ratings that come in at that 4 level. They're supposed to be reviewed now by an engineer as they're coming in through their system.
Great, thank you, Meg. And the member Chapman had asked about the load rating, and I know previously, so did member Graham. Just really quickly, what was the load rating before the 26 tons? Do we know?
There was no posted load prior to the 26 tons, so it would have just been legal loads for that area.
Okay, so that gets me to my question. Is there a requirement or regulation, or I know you said there's going to be guidance by Pennsylvania, but I'm sort of thinking beyond Pennsylvania. Is there any sort of requirement to on some sort of regular interval to check the load rating of a bridge?
It's not required on a regular interval, as you said, but there are certain times and criteria that load ratings should be redone and conducted, such as if there's any design changes to the bridge. Say if you had 2 traffic lanes and really wide sidewalks, and you decide you're going to put in, an additional traffic lane or 2, or if you modify the bridge in any way by extending the width or that type of thing, certainly those would be instances where the load rating would be redone. Condition of the bridge, as we found here in the Fern Hollow case of the Fern Hollow, when you have extensive corrosion or other damage, whether it be from a vehicle strike or that type of thing, all of those types of things can trigger load ratings as well.
I'm going to come back to this, but I am out of time, and so I want to see if member Graham or member Chapman have additional questions in this round.
I'm just ready for the oversight.
Okay, Tom?
No additional questions for me in this round. Thanks.
Okay, great. Mr. Prouty, you mentioned load rating would change on the condition of a bridge. There were a lot of failures here. You had lack of documents to begin with. You had inspectors relying on faulty engineering analysis. You had repair and maintenance that wasn't conducted, certainly a complete lack of oversight. And I think my question is, if you are relying on an inspection to determine whether you should do a new load rating for the bridge, and from my analysis, I think either the city or the state could look at load ratings, you could easily miss something. Unless you're tracking it, which is, I think, where some of our recommendations get into, and we can talk about that in a little bit. What should a meaningful inspection, maintenance, and repair program look like? I mean, we know what went wrong. What should it look like? What's right?
So certainly a big component of that would be preventative maintenance. We know that on bridges, certain things are going to need to be done, such as cleaning out drains, making sure debris is cleared off of bridges, especially if they're made of uncoated weathering steel. Looking at and reading through the inspection reports when they come in and determining what needs to be done to keep things from getting worse. The cost to repair something small now, might not be that much, but when that is allowed to deteriorate and grow over the years, then the costs to fix those things are going to clearly rise and be much more difficult to work with to come up with the type of funding. So preventative maintenance, following the inspection plan, the inspection results and recommendations, and trying to essentially get ahead of things before they become bigger problems.
In this case, were pictures taken of the corrosion area in inspection reports?
Yes, a lot of the areas of corrosion were documented in the inspection reports going back all the way to, again, 2005 when we first started looking at them.
Great. Last question for me in this part. In 2022, there was a regulatory update to the National Bridge Inspection Program. Definitions of some of the inspection types were revised, and the length of time between inspections can now be extended using specific risk-based methods. Now, certainly using risk-based methods, you would hope that would lead you to, in some cases where the condition of the bridge is a problem, more frequent inspections. But could this potentially, if you're not tracking a problem, lead to a greater length of time?
While that certainly is a possibility, I don't think that's not, certainly was not the intent of why they
Sure.
wanted to increase these. The way I see it is when you build a brand new bridge, yes, you'll want to inspect it, the first couple of years to make sure that there's not anything popping up and revealing itself that is going to be a problem. However, that bridge now is very new and it should have, much less problems than an older bridge. So again, it's a way of putting the money where it can be better utilized. So if you don't have to pay for an inspection on this bridge every 2 years, and you can do it every, say, 3 years, that's a way of diverting some of that funding towards maintenance and other things that can be useful.
Yeah, I get that. But if you are not tracking a problem, then it could easily, Dennis, I see you shaking your head, so I'll let you go ahead and answer that.
Chair, I was going to say exactly the same thing you were, that the idea of using a risk-based method to extend the inspection intervals is not a bad one by any means. But the key to that is you have to be assessing the risk properly. You have to be tracking the maintenance issues. You have to be aware of the accurate sizes of the holes in the members. You have to be aware of which are the critical members where a small hole might actually be a much bigger problem than if it was in a different component of the bridge. So it comes back to, as you were going to say, you have to be tracking the risks. And again, hopefully the recommendations we've proposed to the board begin to address that problem and close up the deficiencies that we found here in multiple layers of protections. The holes lined up for the Fern Hollow. Let's close the holes and make sure they don't line up for the next bridge.
Yeah, literally. So with that, that's a great segue to our next section, which is oversight of the bridge inspection program. We'll start with Member Graham.
Thank you, Chair. How can PennDOT in its oversight capacity ensure the city of Pittsburgh takes appropriate and timely action on repair recommendations that are coded as priority 2 through 5?
Thank you for the question, Member Graham. Certainly, our recommendation to the Pennsylvania Department of Transportation to collaboratively work with the city of Pittsburgh to evaluate their effectiveness of the changes post-collapse, we believe will help in this regard, specifically in terms of making sure priority 2 through 5 recommendations are coded properly and action is taken in a timely manner.
So, had PennDOT at any time had any kind of audit program for bridge inspections to confirm the coding was correct and the ratings were correct by the inspectors?
Certainly, the PennDOT has a quality assurance program where they look at approximately 220 bridges per year throughout their districts, and there are 11 districts within Pennsylvania. So that is the mechanism for them to catch catch these deficiencies, and we believe the recommendation for them to evaluate the effectiveness of the city's changes will help in this regard.
Okay. I'm going to go back to something a little bit that Member Chapman talked about a while ago, I think in our first round. The element data for the steel legs were collected during the 2019, 2020, and 2021 inspections. In those 3 inspection reports, all 4 bridge legs were assessed to be CS4 or severe due to corrosion, which warrants a structural review. But we found no evidence that a structural review was ever performed. Whose job was it to do the structural review?
I can answer that question and ask Mr. Prouty add any additional information. Member Graham, you're correct that the steel legs were a condition state 4 in the 2019 through 2021 inspection reports and should have required a structural review. We posed this question to PennDOT, and they could. Their response to us was that the legs were not identified as fracture critical members. Had they been identified as fracture critical members, then certainly a structural review may have been done, or a new bridge loading would have been updated, or would have a new bridge loading would have been assessed.
And who would have been required to do that? Would that have been the city?
Correct.
Okay, with no oversight from PennDOT or anybody else?
Certainly PennDOT would oversee the structural review and would review the updated bridge load rating as part of that process. But since the legs were not identified as fracture critical members, PennDOT indicated to us that's why a structural review and a new bridge load rating was not performed.
Okay. All right. Thank you for that. That's all I have for this round.
Member Chapman.
Thank you, Chair. I'm not sure who is best positioned to answer this question, but I wonder, with respect to bridge inspections and maintenance, I wonder if I could ask someone to briefly describe the relationship and the relative responsibilities of the 3 primary players here, which I believe are the City of Pittsburgh, PennDOT, and FHWA.
Thank you, Member Chapman. The City of Pittsburgh was the owner, and so they were responsible for the inspection and maintenance of the Fern Hollow Bridge. PennDOT was responsible for ensuring that all state bridges comply with the NBIS, including local bridges. FHWA was responsible for the oversight of the state bridge programs in each of the states to ensure that their programs comply with the NBIS.
Thank you, Mr. Walsh. So obviously one of the lessons to be learned here, we have 3 layers here, and yet this slipped through the net. So I know we all hope the recommendations that we're making today will help resolve that, so we don't see similar occurrences in the future, whether in Pennsylvania or anywhere in the country, frankly. This was referenced earlier. We have a draft recommendation today that we'll consider which will call on PennDOT to take the lead in evaluating and publishing a report documenting the effectiveness of changes that have been made by the city of Pittsburgh since the collapse to help ensure that bridges are safe for the traveling public. If this report confirms that the changes made by the city are effective or are proving to be effective, are there communication platforms in place which might help ensure that the findings in the PennDOT evaluation report are widely shared? And I don't mean just in Pennsylvania, but frankly, nationally, if this evaluation yields some findings that might have broader application.
Member Chapman, I can address that question.
Thank you.
Of course, we will be tracking what is happening in PennDOT and in the city of Pittsburgh in relation to the Fern Hollow collapse and their progress on these recommendations. And of course, we will make that information available as they make progress on that. I believe PennDOT would also have the ability to push out information if they have lessons learned. Of course, as staff has been talking about today, there's a number of opportunities here for the lessons learned to be incorporated into FHWA training as case studies. And so that would also be an opportunity to push that forward through training to inspectors.
That's perfect, because really the thrust of my question here is I do believe that there's a role for NTSB in this regard, and certainly for FHWA too. And I look forward to doing whatever I can to help in that regard too, because this was a scary event, and it could have been a lot worse. And there may be some out there that we need to try to catch to make sure we head them off.
Thank you.
My last question here. Another of our draft recommendations will call on FHWA to incorporate the findings from our report on the bridge collapse into their training courses and materials. From some of our previous discussion, it sounds like some of that is happening already. Is that right? I mean, is FHWA already taking some of the well, I mean, obviously we haven't published this yet, but I know that FHWA is aware of some of what has been turned up in the investigation. Are we seeing that already? And do we anticipate that FHWA will incorporate the findings from our report into their courses and materials?
Yes. We've already, we've seen kind of a draft version of their upcoming, the revamped training programs. And they certainly are including more information on like the identification of fracture critical members and that type of thing. So we are confident that these improvements will be made.
And Member Chapman, if I can add to Mr. Prouty's answer, as
Sure.
Chair Hamady mentioned in her opening remarks, one of the benefits of being a party to NTSB investigations is that you get access to that factual information early.
Yep.
So that you can make safety improvements in a timely manner.
Yep, very good. Thank you all very much. Great work. Appreciate your answers to the questions today. Chair, that's all I have. Thank you.
Great, some questions. I want to go back to actually something Member Chapman had asked about on who has authority for what, because it can be very confusing. And we're not going to be issuing this report for a couple of weeks because we will have some editorial changes to it. We'll have a sort of an analysis, a executive summary of it, which we will release later today, but not the details. So who ultimately is responsible for ensuring the safety of the bridge?
Ultimately, that's going to be the bridge owner, which in this case is the city of Pittsburgh.
City of Pittsburgh. And so for PennDOT, the state, they carry out the National Bridge Inspection Program. What else are they responsible for? Why don't I just answer? They are responsible for, just so people are aware, for developing and implementing the bridge inspection policies and procedures, for performing quality control and quality assurance activities, preparing, maintaining, and reporting bridge inventory data, which I'm going to get back to on this, especially as it relates to the National Bridge Inventory System, and or NBIS, and producing valid load ratings, and when required, implementing load posting and other restrictions, correct?
Correct.
Okay. Does PennDOT have the authority to compel the city to perform maintenance, rehabilitation, or replacement of their bridges?
I'll take that one, Chair. Both the federal authority and state authority is limited to specific actions when it becomes a question of public safety. That is why things like the load rating exist, and they're required to be done as the condition changes. When it becomes a safety issue, the state and the federal government can step in. Prior to those switches being tripped, let us say, there's no other direct authority that the state could apply, or the federal government. So
Yeah,
the
they
simplest
don't
answer
have the
is
authority. They don't have the authority to compel maintenance, rehab, or replacement unless there's a issue that they're tracking and conducting oversight of, hey, it's an imminent hazard, an imminent threat to safety, so let's do something. And that's not just for cities, it's also for counties and townships, correct?
absolutely.
Does PennDOT have the authority to close a bridge?
Again, only when those safety mechanisms trip, primarily through, for example, the load posting, or other safety mechanisms like that. But that would be the only time.
Okay. So for federal highways, they issue, now I'm going to go broader, nationally. Federal highways, they issue the bridge inspection standards. They administer bridge inspection training, and they maintain the National Bridge Inventory. I think, Dan, Mr. Walsh, can you talk to me about what information is contained in the inventory?
Yes, Chair Hamady, certainly all bridges that are over 20 feet long are contained within the National Bridge Inventory. And so that's separate from the NBIS, which contains
Yes, sorry about that. Yes.
which contains the regulations for bridge inspection, qualifications of personnel, and bridge
Right.
frequency.
I'm just talking, I got the
Right.
acronym wrong. The National Bridge Inventory.
Right.
What information is contained in there?
It's just strictly the inventory of bridges of each state that are approximately over 20 feet long.
And how is that information used then by states?
Certainly, Chair Hamady, they are categorized by the number of poor bridges. On FHWA's InfoBridge website, there is a categorization categories of poor bridges, fracture critical bridges, the types of bridges. As we've
So
been
the
talking,
condition and the rating is in there.
that's correct.
Okay, that's what I'm
correct.
looking for.
Yes.
So if you're federal highways and you're doing oversight of PennDOT, if you don't have the correct information on the status of that bridge, do you see what I'm getting at here?
I see what you're getting at, Chair Hamady. And so what FHWA uses is a systematic data-driven process to evaluate the NBIS of each state's program using 23 metrics.
Mm-hmm.
And so we looked at this in detail as part of the metrics, and where Pennsylvania was compliant, substantially compliant, non-compliant, and conditionally compliant. That's the measure that FHWA uses to evaluate each state's bridge program. Now, it's in terms of the Fern Hollow Bridge, Chair Hamady, this specific bridge was not identified in the sampling tool that FHWA used. And so FHWA has limited bridges that it reviews. And in performance year 2022, it was 19 bridges out of 1,662 bridges in districts 1 and 12. So it's a limited, very limited population. And we looked at this as part of the investigation, and our recommendation to FHWA to conduct targeted data-driven reviews so that when deficiencies are found, FHWA can expand the population of bridges.
Well, and that was
And
my
so,
question. What if you have the wrong data?
Yeah, certainly.
I mean, if you have the wrong, data on the condition of the bridge, that's certainly, certainly they could look, say, at all poor structurally deficient bridges.
Exactly. And one aspect of the targeted data-driven reviews is to look at whether the load ratings are inaccurate and whether the assumptions used in the load ratings are correct. And I think, in 2017, that's what happened in the state of Mississippi with certain targeted data-driven reviews that led to closure of approximately 378 bridges. So that will tackle that issue. But certainly the issue of the condition ratings that you raised, we feel that the recommendation of the findings of this collapse and the sharing of lessons learned into the bridge inspection training courses will help with the communication between.
Yeah, it'll help with the communication. Right. I'm just thinking about the Federal Highway Administration oversight here. If you have the wrong information to go off of from a data-driven approach, you could go the wrong direction. And this system, this National Bridge Inventory, is used to support federal funding programs for bridge maintenance, repair, and construction. So the information and the accuracy of information and the information you're looking at going forward is critical.
Absolutely.
Okay, so I have two other questions. I do want to thank Turner Fairbank for their, you know what? Actually, hold on. We're just going to go to another section of questions that maybe were not included in any of these 3 rounds. Member Graham, do you have anything?
I have no further questions. Thank you, Chair.
Member Chapman?
No further questions, Chair. Thank you.
Okay, so then my 2 questions are really if you could talk about Turner Fairbank and their work with us and what they do if people are not familiar, who they are.
Turner Fairbank is the research arm of Federal Highway. They look into all aspects of everything that Federal Highway has oversight of, and they look into new technologies. They look into evaluations of new materials, new designs, and that. And they look into the safety aspects of all those as well.
Great, and they worked quite a bit with us on this.
Correct. They not only helped gather the evidence that we needed, they also performed all of the materials testing that we needed to evaluate the steel, and they also looked at all of the welds on the structure, and they assisted us with performing the 3D scanning of the bottoms of the legs that we collected so that we could get the accurate representation of section loss that was on the bridge.
Great, thank you very much. All right, last question. At the end of this, this investigation, we're having the board meeting today. We will issue the final report. Our work, though, does not end at the conclusion of this board meeting. So, Ms. Adler, if you could talk about what we do after the board meeting.
Sure. Thank you for that question, Chair Homendy. After the board meeting, the Office of Safety Recommendations and Communications will work hand in hand with the NTSB staff, with the other board members and stakeholders, including safety advocates, industry organizations, and our federal, state, and local government officials and partners to amplify the recommendations and work to prevent future collapse. The story of this collapse might have been rooted in technical issues, but we intend to present this technical information clearly and concisely to ensure that all the stakeholders and the public understand the recommendations and can implement them. So we'll connect with these stakeholders and recipients of the recommendations to promote them, the recommendations that are adopted today. And we are working to identify outlets for information sharing, such as conferences and trade publications. Then in the weeks that follow the release of the final report, we'll publish a safety website on bridge maintenance, highlighting the findings and the recommendations of this report, and we'll feature the animation from today's presentation. In addition, we'll continue to track and evaluate recommendation responses and work with all the recipients to ensure they understand the recommendations and the actions that are required to further safety. Thank you for the question.
Thank you very much for that. All right, if we don't have any additional questions, we're gonna go ahead and turn to Mr. Curtis. Mr. Curtis, if you can read the proposed findings.
Certainly, Chair. As a result of this investigation, staff proposes 19 findings. Number 1, none of the following were factors in the collapse. 1, the use of uncoated weathering steel. 2, the design of the bridge. 3, the fabrication materials. 4, the deterioration of the welds. Or 5, the qualifications of the 2005 through 2021 bridge inspection team leaders. Number 2, the emergency response was timely and adequate. Number 3, the Fern Hollow Bridge collapsed due to the extensive corrosion and section loss of its fracture critical members, specifically the transverse tie plate, resulting in the failure of the southwest leg, E1R, which no longer had the structural capacity to carry the bridge's loads at the time of the collapse. Number 4, the significant corrosion and section loss on the southwest leg, B1R, resulted from the failure of the City of Pittsburgh to act on the repeated maintenance and repair recommendations documented in inspection reports from 2005 to 2021, leading to progressive deterioration and structural failure. Number 5, in response to National Transportation Safety Board Safety Recommendation H-23-13, the Federal Highway Administration developed a risk-based, data-driven process and encouraged its use by state departments of transportation, as well as federal agencies and tribal governments that own and operate bridges, to help them identify, prioritize, and perform follow-up actions documented in inspections of bridges with uncoated weathering steel components. Number 6, multiple inspectors of the Fern Hollow Bridge, contracted by the Pennsylvania Department of Transportation on behalf of the City of Pittsburgh over a period of more than 15 years, failed to 1, clean corrosion before measuring, 2, accurately quantify remaining material, 3, accurately rate the general bridge superstructure condition, and 4, recommend a structural review of the bridge legs. And these failures contributed to the bridge's inability to support the loads it was rated for before the collapse. Number 7, in the fracture critical identification framing plans, the fatigue and fracture bridge inspection plan, and the handwritten notes contained in the earlier Fern Hollow Bridge inspection reports, Pennsylvania Department of Transportation contractors did not properly identify the bridge legs, including the transverse tie plates, as fracture critical members, non-redundant steel tension members, and as a result, the legs did not consistently undergo a more in-depth, hands-on fracture critical member inspection as required by 23 Code of Federal Regulations 650 Subpart C. Number 8, had the bridge legs including the transverse tie plates, been properly identified as fracture critical members, the inspection recommendations related to repairing and reinforcing section loss and holes in the legs would likely have been assigned a priority code of 0 and prompted action within 7 days. Number 9, if the city of Pittsburgh had taken appropriate action to repair or reinforce the section loss on the fracture critical bridge leg components, the collapse of the Fern Hollow Bridge could have been prevented. Number 10, the correct identification of fracture critical members is crucial to ensuring that these members are properly maintained so that they do not fail and result in a partial or full bridge collapse. Number 11, bridge inspectors lack adequate guidance from the Federal Highway Administration Bridge Inspectors Reference Manual and the American Association of State Highway and Transportation Officials Manual for Bridge Evaluation on the proper identification of localized tension zones and tension components to correctly identify fracture critical members in preparation for and during bridge inspections. Number 12, the calculations and assumptions used in the 2014 load rating analysis overestimated the Fern Hollow Bridge's capacity. And if these calculations and assumptions had 1, correctly accounted for the amount of wearing surface on the bridge, 2, used the correct K factor to estimate axial load capacity, and 3, correctly accounted for the localized effects of section loss, the result would have required the closure of the bridge. Number 13, the quality of the city of Pittsburgh's paving records was so poor that determinations could not be made about whether the actual asphalt wearing surface exceeded what was assumed in the design of the bridge, or about how long the wearing surface had exceeded the as-designed thickness, which contributed to an incorrect load rating analysis. Number 14, the thickness of a bridge's wearing surface is an important component for calculating load ratings, and non-destructive techniques can provide a means of verifying the actual thickness of the wearing surface without introducing damage to the bridge. Number 15, the post-collapse actions completed by the city of Pittsburgh in response to its failure to maintain the Fern Hollow Bridge, which resulted in the bridge's collapse, increased staff in the Bridges and Structures Division, a streamlined funding process for bridge maintenance and repairs, review of load ratings, and approved funding for bridge rehabilitation projects, have the potential to address the deficiencies found in this investigation, including insufficient oversight of needed bridge maintenance and repair activities. Number 16, the Pennsylvania Department of Transportation's insufficient oversight of the city of Pittsburgh's bridge inspection program contributed to the bridge's continued deteriorated condition that led to the collapse. Number 17, the post-collapse actions completed by the Pennsylvania Department of Transportation conducting field examinations of fracture critical K-frame bridges, conducting the file reviews of other K-frame bridges and bridges with steel pier bents, and publishing a technical bulletin updating Pennsylvania's Bridge Safety Inspection Program and its Bridge Maintenance Program, have the potential to identify at-risk bridges throughout the state, but is also necessary to provide proper oversight, including ensuring that maintenance and repair recommendations are properly coded, monitored, and completed in a timely manner. Number 18, the Federal Highway Administration should use data-driven reviews of targeted bridge populations to investigate specific bridge safety issues, such as the validity of load ratings of bridges with advanced deterioration. Number 19, the Fern Hollow Bridge collapse demonstrates the consequences of failure to complete inspections in accordance with standards, failure to correctly identify fracture critical members, failure to correctly perform a load rating analysis, and failure of the bridge owner to respond to inspection findings and complete maintenance recommendations in a timely manner. Chair?
Thank you very much, Mr. Curtis. And now I'll ask Member Graham and Member Chapman to go ahead and turn on their cameras, and you can keep them on throughout the discussion. All right. Are there any amendments to the proposed findings? Motion to adopt the findings and a second.
So moved.
Second.
Great. Moved by Member Graham, seconded by Member Chapman. We'll take a vote to adopt the proposed findings. Council?
Yes, Chair, thank you. Board, if you're in favor of the proposed findings, please say aye, and if opposed, say nay. Member Graham,
Aye.
Member Chapman,
Aye.
and Chair.
Aye.
All right, the findings are, the recommendations are 3 in favor, Chair.
Thank you so much. The findings are adopted. Mr. Curtis, can you read the proposed probable cause?
Certainly, Chair. Staff proposes the following probable cause. The National Transportation Safety Board determines that the probable cause of the collapse of the Fern Hollow Bridge in Pittsburgh, Pennsylvania, was the failure of the transverse tie plate on the southwest leg of the bridge, a fracture critical member, non-redundant steel tension member, due to corrosion and section loss resulting from the City of Pittsburgh's failure to act on repeated maintenance and repair recommendations from inspection reports. Contributing to the collapse were the poor quality of inspections, the incomplete identification of the bridge's fracture critical members, non-redundant steel tension members, and the incorrect load rating calculations for the bridge. Also contributing to the collapse was insufficient oversight by the Pennsylvania Department of Transportation of the City of Pittsburgh's Bridge Inspection Program. Chair?
Thank you so much, Mr. Curtis. Are there any amendments to the probable cause? No? Do I have a motion to adopt and a second?
So moved.
Second.
Great. Moved by Member Chapman, seconded by Member Graham. And Council?
Yes, again, members, I'll start with Member Graham,
Aye.
Member Chapman,
Aye.
and Chair.
Aye.
All right, Chair, the vote tally is 3 in favor of adopting the probable cause.
Great. And Mr. Curtis, can you read the proposed recommendations?
As a result of this investigation, staff proposes the following 11 new safety recommendations. 5 to the Federal Highway Administration. Number 1, require state departments of transportation, as well as federal agencies and tribal communities that own and operate bridges, to conduct a one-time review of the existing fracture critical member, non-redundant steel tension member, inspection plans for the bridges with non-redundant steel frame leg designs in their inventory, and update these plans as necessary to ensure that all fracture critical members, especially those in the legs, have been properly identified and accounted for in the fracture critical member inspection plans and inspections. Number 2, update your bridge inspector's reference manual to include guidance that addresses the identification of localized tension zones and tension components in non-redundant steel members that are generally considered to be fully or partially in compression. Number 3, update your bridge inspector's reference manual and bridge inspection training courses to include reference material on the selection, frequency of use, and application of non-destructive inspection methods for assessing the wearing surface thickness on bridge decks. Number 4, establish a process for conducting targeted reviews of the safety issues identified in this investigation to include at a minimum 1, an evaluation of bridge owners' determinations of the need to conduct new load ratings of bridges with advancing deterioration, and 2, an evaluation of inspection reports on bridges with advanced deterioration to determine if the assumptions and methods used in the load rating calculations are correct, and incorporate the results of these reviews into the National Bridge Inspection Program Compliance Review Manual as necessary. Number 5, incorporate the findings of the Fern Hollow Bridge collapse investigation into your bridge inspection training courses and use the Fern Hollow Bridge as a case study to emphasize the need to complete maintenance and repair recommendations from inspection reports. Follow the guidance to ensure that bridge inspections are properly performed, correctly identify fracture critical members, and correctly calculate load rating analyses. 2 recommendations to the Pennsylvania Department of Transportation. Number 6, work with the City of Pittsburgh to evaluate and publish a report documenting the effectiveness of the changes made by the City of Pittsburgh to ensure that bridges are safe for the traveling public. Evaluated changes should include completing necessary bridge maintenance and repair recommendations and confirming that bridges have correct load ratings that account for deterioration. Number 7, develop and implement a plan to publish yearly aggregate data on bridge maintenance and repair recommendations to monitor completion of these recommendations. 2 recommendations to the City of Pittsburgh. Number 8, establish a system to ensure that you maintain paving records indicating how much asphalt wearing surface is removed and how much is subsequently placed during every bridge resurfacing operation. Number 9, in collaboration with the Pennsylvania Department of Transportation, evaluate the effectiveness of the changes made by the City of Pittsburgh to ensure that bridges are safe for the traveling public. Evaluated changes should include completing necessary bridge maintenance and repair recommendations and confirming that bridges have correct load ratings that account for deterioration. 2 recommendations to the American Association of State Highway and Transportation Officials. Number 10, update your manual for bridge evaluation to include guidance that addresses the identification of localized tension zones and tension components in non-redundant steel members that are generally considered to be fully or partially in compression. Number 11, update your manual for bridge evaluation to include reference material for the selection, frequency of use, and application of non-destructive inspection methods for assessing the wearing surface thickness on bridge decks. Additionally, staff proposes classifying the following previously issued safety recommendation to the Federal Highway Administration. Recommendation H-23-13, develop a risk-based, data-driven process and encourage its use by state departments of transportation, as well as highway bridge owning federal agencies and tribal governments to help them identify, prioritize, and perform follow-up actions documented in inspections of bridges with uncoated weathering steel components. Safety recommendation H-23-13 is classified closed acceptable action in section 2.3 of this report. Chair?
Thank you very much. Are there any amendments to the proposed recommendations?
Not for me,
Nope.
thanks.
I have 2 amendments. Mr. Curtis, could you pull up recommendation number 6? Or whoever is working the document. Okay, so the first one is to recommendation number 6. There was some confusion about who would lead the effort to evaluate and publish a report documenting the effectiveness of the changes made by the City of Pittsburgh to ensure that bridges are safe for the traveling public. Pennsylvania DOT has the oversight authority, so we want to make that very clear. Staff had suggested language. Originally, there was different language provided by highways than provided by safety rec. So I think we should make sure that the Office of Highway Safety is satisfied with the recommendation. But my amendment right now would strike work with the City of Pittsburgh to, and then insert lead the effort So then it would now read to the Pennsylvania Department of Transportation, lead the effort to evaluate and publish a report, and the rest would be the same. So it's now open for discussion. Recognizing myself again, this was brought up after responses were provided to members in response to comments to the draft. So staff needed to submit this for clarification in the board meeting. Again, after your comments, I'm going to ask staff if they are comfortable with how it's currently drafted or if they need to make any changes. But with that, any further discussion?
None.
All
I
right.
support- I support it subject to staff.
Yep. Chris?
Staff agrees. We appreciate the clarification.
Okay, great. So you're okay with it removing the city of Pittsburgh?
Yes, yes.
Okay.
We're okay with the PennDOT taking the lead. And then I think we'll talk about the city of Pittsburgh working with them as well and how you're proposing to amend that one as well. But we think that the lead the effort will be clear that PennDOT will be leading the effort, but they will also work with the city of Pittsburgh to do that.
Okay, great. Is there any objection, council, to me offering the next amendment and just doing a vote in block?
No, there's not, ma'am. We should probably just confirm that you've got a second to the motion to
Oh,
amend.
yeah. Do I have a second to the amendment? Sorry,
Second.
Mike. Oh, I think, okay. Tom, thank you, Tom.
Yep.
Thank you, Mike. Second, thank you for that. Okay, so then without taking the vote, Brian, Mr. Curtis, can you bring up recommendation number 9? This, again, wouldn't be much of a change. My amendment would strike the words in collaboration. So, and insert the word work. So now it would state work with the Pennsylvania Department of Transportation to evaluate the effectiveness of the changes made by the city to ensure that bridges are safe for the traveling public, and the rest would be the same. I will turn to staff, but I don't have anything more here, but first, anything from Member Graham or, oh, is there a second?
Second.
I think Mike actually whispered second, so we'll go with that, Member Graham. You're on mute.
You're muted, Mike.
Sorry, I second that.
Okay, thank you. Any conversation about it or go to staff? Okay, Ms. Poland?
Yeah, staff is fine with this. We think it's an equivalent change, so that goes along with the First Amendment, and we're fine with that.
Great, thank you so much, and thank you for clarifying these. We will go ahead and vote on the 2 amendments, the amendment to recommendation 6 and the amendment to recommendation number 9. And council.
Yes, ma'am. Members, as usual, if in favor, say aye, and if opposed, say no. Starting with Member Graham.
Aye.
Member Chapman
Aye.
and Chair Homendy.
Aye.
All right, Chair, obviously the tally is 3 in favor of adopting the amendments proposed to recommendations number 6 and 9.
Any further amendments to the recommendations? No. And so we should, since we just adopted the amendments, we have to vote on the entire proposed recommendation package. Council.
All right, members, again.
So is there a motion and a second on that?
So moved.
Second.
Moved by Member Chapman, seconded by Member Graham.
Thank you, Chair. All right, board, if in favor, say aye. Opposed, say no. Member Graham,
Aye.
Member Chapman,
Aye.
and Chair.
Aye.
So 3 in favor of adopting the recommendations as amended.
And Mr. McMurray, just go ahead and keep your
Sure.
screen on, because we're going right to the report, which would be the report as proposed and also amended. Are there any amendments to the draft report? No? Okay, do I have a motion to adopt the final report as amended?
So
Not
moved.
amended.
And,
Second.
okay. Adopt,
I think that was as not amended, correct, Chair?
I think the entire final report would include the recommendations,
Oh,
so
okay. The amended
it was
recommendations.
amended. Okay, great. Offered by, or a motion offered by Member Graham, seconded by Member Chapman. And the final vote, go ahead.
Final vote, Member Graham,
Aye.
Member Chapman,
Aye.
and Chair Homendy.
Aye.
All right, Chair, 3 in favor of adopting the report as revised or amended.
Great. Do any members reserve the right to file a concurring or dissenting statement? No? Okay. So with that, our deliberations have now concluded. I want to thank my fellow board members, Member Graham and Member Chapman, for their preparation and participation in today's meeting. We discussed important topics that will benefit the final report and inform our safety recommendations. I want to do something I don't believe I've ever done at a board meeting, which is share a line from a work of fiction. This is from a 1990 Kurt Vonnegut novel. Another flaw in the human character is that everyone wants to build and nobody wants to do maintenance. Let me repeat that. Everybody wants to build and nobody wants to do maintenance. To see just how much this applies to Fern Hollow, consider this. The bridge has since been rebuilt. In fact, it reopened to traffic for the first time in December 2022, 11 months following the collapse. All 4 traffic lanes have been open since July. Following 17 years of unheeded maintenance recommendations, the bridge was rebuilt in 11 months. 17 years, 11 months. But humans, entire communities in the city of Bridges, they can take longer to recover. Again, our hearts are with those who were injured in this catastrophe, as well as those who regularly travel the Fern Hollow Bridge. We cannot prioritize new construction over maintaining our nation's roads, bridges, and tunnels that we all traverse every single day. The collapse of the Fern Hollow Bridge is an example of the stakes. When I was on scene, I crawled under the debris and it was devastating. Had it not been snowing, there would have been school buses full of kids and countless commuters walking, biking, or rolling across the bridge on the morning of the collapse. It's clear that the Fern Hollow catastrophe was a serious wake-up call for both the city of Pittsburgh and PennDOT. I hope it serves as a wake-up call to every other bridge owner and state. Our report outlines the positive steps each entity has taken to address the deficiencies found in this investigation. While these efforts have the potential to prevent another bridge collapse, we need to make certain that bridges are safe for the traveling public. That's why the NTSB has recommended PennDOT evaluate the effectiveness of the changes made by the city. We're also calling on PennDOT to track and monitor the status of bridge maintenance and repair recommendations to ensure they're completed. A public, transparent system is vital to ensuring all recommendations are addressed, not just the most critical, so they don't fall off PennDOT's radar, to borrow a phrase from the Assistant Chief Bridge Engineer. We also made 2 recommendations today that will ensure the city of Pittsburgh keeps more complete paving records and correctly calculates bridge load ratings. Everybody wants to build and nobody wants to do maintenance. I hope our investigation changes some minds about that. We cannot take our infrastructure for granted. Lives depend on it. With that, I'd like to extend the board's thanks to the NTSB team, including our colleagues in the Office of Highway Safety. the Office of Research and Engineering, and the Office of General Counsel for their work over the course of this investigation and in the development of an excellent report. We also express our appreciation to our colleagues in the Office of Human Capital and Training, the Office of Chief Information Officer, and the Digital Services Division for their vital support of this meeting. Finally, I'd like to thank the Office of Safety Recommendations and Communications for its diligent work and advocacy to improve safety. When acted upon, the recommendations we've issued today will save lives. Going forward, the NTSB looks forward to working with the Federal Highway Administration, the Pennsylvania Department of Transportation, the City of Pittsburgh, and the American Association of State Highway Transportation Officials to implement our recommendations. At the same time, NTSB will not stop working to create a safe transportation system where there is no longer a need for our recommendations. Thank you, and we stand adjourned.